yeah, find some different themes. Oh, can everyone say, "What's up, YouTube"?
What's up, YouTube?
That was a trick.
Now you appear to be live.
The answer was you cannot say that. Okay. How many minutes does it take someone with a CS doctorate to go live on YouTube? 22. Which is, what's the prime factorization of 22? 2 times 11. So in the olden days, there didn't used to be division, and there is now. We're sort of all living in the world that division created, right? Is that my fault? No, I voted to only have operations that made numbers larger, right? I thought numbers should monotonically increase, right? And subtraction was the first mistake. We can all agree with that, right? But they snuck in the door by what they do. They said, well, what if I just add a negative number to a positive number? And I said, I don't really do negative numbers, right? So I was like, so they're like, well, only the people with negative numbers will have subtraction. I was like, that's fine. We can just leave them over there. And then they're like, what about multiplication? Have you ever wanted 3 of 4 things? And I was like, well, yeah, that's a great number of things to have. That's how many hours in the day you have other than the other 12, right? And so I was like, fine, like, yeah, I guess like multiplication, I can see that accomplishing things. It's just addition over and over again, right? So that should be totally fine. I don't see what problems that would cause, right? And then they're like, have you ever wanted to undo a multiplication you did? And I was like, yeah, I've made mistakes before. I mean, not many. I can't count them, of course, because my numbers only go up, right? So I'm not very good at counting things, right? And they're like, what if we had something that did like multiplication but backwards? I was like, I'm listening. And then I found out they were talking about division the whole time, and I was very upset, but they got their foot in the door, right? It was too late for me. And so the person that did this was named Euclid. And this wily, conniving person, probably a communist, this person invented division with repeated subtraction, completely bamboozling everyone who let subtraction in the door. See, I drew the line at subtraction, so that one didn't get me. They did the reverse multiplication trick on me. Anyways, Euclidean division is cool. And it's cool because unlike a lot of operations, so I mentioned a lot of operations make numbers bigger, right? And that's good, right? So that's what you want to happen to the stock market, right? What else is supposed to get larger? That's the only thing I can think of right now, actually. And that's because you take 2 numbers and you get 1 number back. Euclidean division is completely different. It accidentally gives you 2 numbers back at a time, right? It's like a 2-for-1 special. This seemed a little bit sketchy, and I think people started doing this before return types existed, so there wasn't really a good way to write this down. But anyways, maybe this person from ancient Greece said it was okay. We don't actually know, right? I don't know. It's named after Euclid. So today I'm going to introduce Euclidean division using a variety of motivating examples. Then I'm going to introduce the Euclidean algorithm, which is an algorithmic way to do Euclidean division if you don't have division already, which we're assuming. Then we're going to do the extended Euclidean algorithm, which is going to solve every problem we have. And it's going to give us Bezos identity. And I believe you pronounce that similar to the oligarch, but I'm not absolutely positive. And we don't like that oligarch. We have our own oligarchs here in Oregon. Here in Oregon, our oligarch is Phil Knight, right? And he watches out for us and he protects us and he has our best interests at heart. Unlike big, mean Jeff Bezos up in Seattle. Can I get some loud booing for Seattle?
He's actually in Florida.
Okay, that's fine.
Anti-Seattle, pro-Florida is a bold position to take.
No, I'm Florida neutral.
Oh, Florida neutral.
Yeah.
Okay.
Yeah, you know, Portland as an ascendant regional power mostly has to deal with its local rivals, right? Which are, and I think Portland is way better than both of these 2 places, and you will too when I say their names. Seattle and San Francisco. Okay, so that was a bad example. Let's compare ourselves to Gigi, right? Okay, but every once in a while I look up like concerts in this area, and they're like, they do like 2 nights in Seattle and 2 nights in San Francisco and skip Portland, and I was like, I commend them on their spot on analysis, right? I think there's probably more than 4 times as much money in both of those 2 places as there is here, right? Anyways, my partner's going to see Poppy at the Crystal Ballroom tonight. Anyone know Poppy? Did a Poppy, P-O-P-P-Y, did a collab with Knocked Loose, did a collab with Bad Omens, okay? bit of a screamer. Okay, this is the problem we're trying to solve. There's fast ways to do this. Really? There's fast ways to calculate the least common multiple of numbers that are one less than a prime? Yeah, in fact there is. And we will show that today using this little Euclidean algorithm thing. As previously reported, I asked a very, very expensive, actually, I think this algorithm cost $4 trillion. I said, what do you think I want to see when I ask you what a GCD is? And it says, oh, no problem. You want to see this code right here. I said, no, that's actually correct. That is correct. Your training was well done. I did, in fact, want to see a little tiny while loop. And so I don't know a great way to implement the least common multiple without using the GCD. There's one little division snuck in there, but we don't have to acknowledge the legitimacy of that right now. We can come back to that a little bit later. And the way this works is you just keep taking the bigger value modulo the smaller value, and then keeping track of both values. And sort of you just divide off and break off chunks over time. Does that seem confusing? Don't worry, I have slides on it. Okay, so that's what we're doing today. The other thing we did, we found the LCM of p minus 1 and q minus 1, right? And that was good fun. That was Carmichael's totient function, and it was not a component of our private or public key. It was a value we used later on to find other things. And specifically what we used that value in is we used it to find D, the decryptor, right? So let's organize our thinking. RSA takes messages and it encrypts them. And how does it encrypt them? It encrypts them the way that everyone can encrypt them. So they use a public key, which I call E, the encryptor. They take the message, which they store as a numerical value, and I should have convinced you can store anything as numerical values in the message, like signals, officer stuff, right? Like everything is just information in some way. Cited Claude Shannon, right? But, and so I check my message, it's some number, I raise it to a power, that power is E, that power is posted publicly in my Twitter handle, and I'm Glenn Greenwald, so everyone in the world sees all my tweets, right? Twitter power user, one of the highest scores on that website, right? And then what happens? Well, then I send this message to whoever I'm sending it to, right? And that person has to unencrypt it, and they just get a pile of bits comes out of the pipe in their wall, right? And they're like, oh no, all of these bits, good thing I know exactly what order they're in, which is the only thing I need to convert them into information. And I take those bits, I treat them as a number, and I raise them to the power D. D is the multiplicative modular inverse of E, the encryptor, modulo lambda, Carmichael's totient function. How do you find the multiplicative modulo inverse of something? Well, what we did here, and this also has the helpful benefit of explaining to you what the multiplicative modular inverse is the multiplicative identity is 1. Why is that? Because when I multiply something by 1, I get that thing back. So that means it's the identity. And so if I want to have the multiplicative inverse of something, it is the thing by which I multiply that value to get 1. So x times y equals 1. X and y are multiplicative modular inverses of each other. There's also additive inverses, which are known as the negative numbers, right? So one way to do this is I just guess a number. So D is my guess. I multiply it by E, and I check to see if it equals 1. But I'm doing a little bit of a wrinkle here, because I'm not just looking for multiplicative inverses. So the multiplicative inverse is usually pretty easy. You take 1 divided by that thing. The multiplicative inverse of 2 is 1/2, right? As you know, I don't believe in fractional numbers, right? I only believe in the natural numbers, except sometimes I believe in the integers when it's temporarily convenient, and I try and make sure no one notices I was doing that, right? These things are all natural numbers, right? So in order to find two natural numbers that when they're multiplied by each other equal 1, well, there's not a great way to do that, but I can write a loop that does that, where I just keep picking bigger and bigger numbers and multiplying them together to see if they happen to be essentially what is 1 more than a multiple of this number, right? I need a remainder of 1 when I divide by that number. So I'm going to multiply two numbers together, I'm going to divide them by something, and I'm going to hope I get 1 back. What that means is when I raise my message, e to the d, message to the power of e to the power of d, right? I'm essentially raising it to the power 1 with respect to this value. And m to the first power is itself, because that's the exponential identity, right? So I get back the same message I put in. That's the basis of RSA. This is how you find the multiplicative modular inverse if you're bad at things, right? And we're bad at things, which is why we're not allowed to use our code in this class, but we're going to look up what we would do if we were good at things, right? Does everyone remember RSA? You good on RSA? We're locked in? Okay. We used modular exponentiation, and just going back and forth here to point out that I'm doing a lot of things where I multiply and then take a modulo, right? This is the fundamental basis of how we get things to work in RSA. We multiply things together and we take a modulo, right? So, we all have the same problem here. And this same problem is the same problem we were trying to solve partially with 409060, and that is caused by 409060, which is that when I multiply numbers together, I need more bits to store the result. And so if I keep multiplying numbers together, I keep needing more bits. And I don't have an infinite number of bits. I have a very specifically finite number of bits. So if I multiply two 4096-bit integers together, either I lose information or I find twice as many bits as I started with. In this class, up until this point, I very specifically have gone out of my way to prevent you from knowing how to ask the operating system to give you an arbitrary number of bits. That's not allowed. There are, in fact, ways to do that in C, and you should not use them because they are something that's called unsafe, right? And so instead of doing that, we're simply just going to not use those numbers. We're just going to get everything we need done in smaller numbers, and those smaller numbers are going to be at most 4096 or whatever you specify, right? You can just as easily, when you finish writing your 4096 library, in fact, I developed mine this way. I developed mine on 512 bits. It was much easier. And then I just went up to 4096 when there were no bugs left, and of course everything worked, because it's unlikely you can do 512 bits successfully and not 4096. You find one case where you didn't use a constant that you should have, right? One magic number in your code and you find it pretty quickly. So we have, with specifically modular exponentiation, a version now of exponentiation where I can take a number, square it, or raise it to any other power, and not increase the number of bits I need to store that number. Because I will never need more bits to store that number than I need to store n. Right? So I could add some bits for a while, right? But I'll never need more bits than there are bits in n. Now, my working values might be larger, because I might need to multiply two numbers as big as n times each other, get many bits, and then perform the division, right? So n doesn't fix the number of bits I might need to work with, but it does fix the number of bits that I need to return. So internally within inside modular exponentiation, I might have much larger numbers, right? One of the other things you may have noticed, and I'd encourage you to think about this, I don't know how much you all think about what might cause your code to be slow, right? But when I performed a big multiplication, I multiplied every chunk of 32 bits by every other chunk of 32 bits. Which means that when I was taking 4096 bits, I had 128 chunks of size 32, and I multiplied them all by each other, which means I took 128 squared multiplications. Now, if I did not cap my size at 4096 bits, but I capped it at 8192 bits, which is the next power of 2, I broke that into 32-bit chunks. Why 32 bits? Because I have a 64-bit multiply, which is big enough to store the product of 32-bit values, right? Then I would need 256 chunks. And that might feel like it's twice as slow. No, it's much worse than that, because I was performing 128 squared multiplications. 128 squared is 2 to the 7th, or 128 is 2 to the 7th, so 128 squared is 2 to the 14th. 256 squared is 2 to the 8th squared, which is 2 to the 16th, so instead of the 14th. So it is 4 times as many, right? Which means that every time I double the size of my integers, my multiplication slows down by a factor of 4. What this should mean is that no matter how fast my multiplier is, it is going to run out of speed very, very quickly, right? And the other thing that is going to happen, right, and not with us necessarily in this class, is not all of the memory on my computer is the same speed. Some of you know about solid-state drives and hard drives, and you know that perhaps one of those is smaller and faster, right? This continues all the way up the memory hierarchy to working spaces of very, very small sizes located physically in the same space that your computer is performing computation, right? So you're going to receive big drop-offs in performance costs one of the times you double, right? We felt this very sharply when I was looking up how big numbers were, and Python suddenly slowed to a crawl exactly when I asked for things of 31 bits in size, right? There's these breakpoints, right? So you're going to hit breakpoints while your costs are increasing exponentially. All of this is bad for you. So you should be extremely convicted of the value of keeping your numbers as small as possible. Separately, you need your numbers big enough to store any secret at all, right? So what you really want is you want things at the exact right size. And the exact right size, according to GitHub, is 4,096 bits. And I don't see why we would disagree with them, because we don't know what we're doing, right? But it is in fact true that plenty of other websites accept 2048 size keys. So, I don't know. I think GitHub is probably under more concerted attack than many websites, right? This is how I implemented my big div. I have omitted the actual code, but I want to show something that is going on here with function types. When I take add, my big add, I had 3 arguments or parameters. You can call them whatever you like. We'll call them perhaps A, B, and C, right? There is no built-in or default or even nice way in the C programming language to return 4,096 bits of something. There are ways to return the location of 4,096 bits of something and hope that you keep track of it. There are ways to tell the C compiler that you are going to be passing around chunks of size 4,096 bits and hope it works in your operating system, right? All of these things are possible. None of them are something I would recommend. What I found it much easier to do is say, whoever is doing the big math is responsible for holding the big numbers. And so you, if you are writing main, your main function in your .c file, you're responsible for keeping track of these groupings of 4,096 bits. And in the case of using add, you're responsible for keeping track of 3 of them. 2 of them hold the addends, which I think is what I should call the numbers I add together. And then 1 of them is going to hold the sum. I'm responsible for loading up the addends with the values that I want to add together. I don't have to do anything with the sum. My big add function took care of the sum. It deleted everything that was in there and put in the new number when I was done. And this worked very well for add, which takes 2 numbers and is going to populate the value of 4,096 bits that I provide to it. Subtraction does the same thing. Multiplication does the same thing. And my multiplication just so happens to be a modular multiplication where I do not return 8,192 bits, right? But I could. It would be a simple change to the code, right? This doesn't work with division because all over the place in RSA, I both have to divide values and I have to take the modulo of values, but both of those operations are the same. So I performed this form of code factorization. But this form of code factorization is actually highlighting like a deeper underlying truth about the way division works, which is that division is fundamentally different from the other operations and that it does not work on integers. It simply does not work. You cannot divide integers reliably because when I add 2 integers together and then subtract the results, I get back one of the original integers. When I subtract 2 integers together and add the result, I get the original integers back. When I multiply 2 integers together and I divide, I do not necessarily get the same values back due to rounding. Because when I divide 5 by 2, there's just no way to deal with that with integers, right? And so the way we're transiently dealing with that with integers is we're keeping track of quotients and remainders, and we're returning some of them in our buckets of bits. So I'm going to use 3 different ways to refer to division. You're aware of division, so I don't need to overly belabor this, but I am also going to try and introduce the number theoretic sense of what's going on here, right? And I'm going to use this with these things here. This is Q He used the rational numbers. Those are the numbers that can be found by dividing integers by each other. And this is R. This is all of the numbers. That includes pi, and Q does not. So I cannot get to pi with division. I think I have to use, does anyone know, do I have to use exponentials or polynomials? I have to use one of the two. Pi is a transcendental number, and it is much harder to describe than other numbers. There are non-terminating decimals. I think 1/7 is a non-terminating decimal. Very easy to get access to non-terminating decimal values, right? Pi is dramatically more poorly behaved, and there is no way to store pi in a computer. We can store the idea of pi, we can store functions that return pi, we can store ways of calculating pi, but we cannot store all of the digits of pi. We can, in a sense, store all of the digits of 7 by simply implementing base 7 arithmetic in a computer, which would be very inefficient, but is completely possible to do, right? So naive division is, I think, the division I learned in elementary school. I remember at some point talking about remainders, and I'm wondering now if my elementary school teacher just happened to only ever have me divide things that were integrally divisible by each other, so I didn't know which form of division I was using, right? But in practice, when I go around and I talk to like humans, right? And there's like, say, 3 of us, and we agree to split a $20 bill. A $20 bill is overloaded. A $25 bill. So a bill at a restaurant, not a physical piece of bill, is the idea I'm trying to predict. So if 3 of us go out to dinner and the bill is $25 and we split it 3 ways, we sort of understand intuitively that we're going to be getting some weird behavior with the numbers, right? One of us is going to have to find 1/3 of a penny, right? Or perhaps 2 of us, right? And so my sense is, like, when I say to another human, hey, can you split this 3 ways? They're doing this kind of division, and they are not thinking about, and they do not care about the fact that perhaps that division is not even expressible in any of the units we have access to, right? We'll figure it out never. We sort of do lazy evaluation or something like that. Maybe we approximate at some point, right? But fundamentally, under the hood, we're just going to use all of the means at our disposal to get as close to a non-integer approximation of the division as possible. And I think youths, like children, do this as well. Like when you ask them to divide up a cake, right? They really go for absolutely atomic precision, right? They don't say like, well, I'm going to cut the cake into 4 quarters, and there's 5 of us, then we'll just like try and smoosh like pieces together. Like humans don't do this, right? So I call this naive division because I think this is the division that happens in humans' minds. Known Python defender, Calvin Deutschwein, naive division is performed with a single slash in Python. That's great because Python is a natural language. It is the language that children learn to speak while they're growing up, right? So this makes sense as a design decision, right? For example, in my undergraduate class where I teach Python, there's a bunch of 19-year-olds that are learning to speak for the first time. Is this recording? That is recording. Okay. And I cherish all of them as much as I love myself. In the C programming language, which was designed for adults that were not trying to communicate with each other, we use the single backslash also for division, but only if we're providing fake made-up numbers called floating point numbers, right? And everyone hates floating point numbers. If you don't know why you hate floating point numbers, don't worry about it. Just take it on faith from me. Just, if you're in a coding interview, say, floating point numbers, and see if you get the job. I've heard this works. It happened to me, and then I ended up doing rocketry, which was very precise. So maybe that only works in some fields. So C also uses single forward slash. It's just like Python if you're using numbers for weaklings and cowards, right? This is embarrassing, right? I saw someone whose name I don't want to call out, who was trying to take a square root in the C programming language, right? C programming language, square root looks for floats, right? And should you ever take a square root in a programming language? Of course not. That's a ridiculous thing to do, right? Because you can just square numbers, right? And squaring numbers is easy. It's multiplication. We already learned about that, right? So if you ever think you should be using a square root, you should realize you're wrong well before you post it in Helpline, right?
God forbid you try and follow an algorithm faithfully.
I think that you didn't have to use square root to follow the algorithm faithfully.
You didn't, but it seems like the right thing to do at the time.
I've been wrong before too, I understand. Okay. Not often. No. So I looked at the Python double slash, and my brain compiled that into a C++ style line comment. Did that happen to any of you? Okay.
Yeah. A lot of errors on the tester for those style comments.
Yeah, that completely cooked me. Anyways, integer division is like the cool, good kind of division that people use that do discrete mathematics, right? And so there's two kinds of mathematics, continuous and discrete. Discrete's the good kind, right? I don't even know if I can defend that. The discrete mathematics is the kind computers can do because they can't do infinite precision anything, right? So frequently, I think there's been some discussion whether the universe is discrete or continuous, and I don't know why. It's clearly running on Turing machines, right? So it's necessarily discrete. But many people incorrectly believe it's continuous, probably as a result of, I don't know, being scientists or something. And so I always like to do integer division. And why is that? Because when I'm out with my friends, which I do have, and we split a $25 check 3 ways, I realize immediately that that's impossible, and I humbly volunteer not to pay my share. So it can be evenly divided into 2 shares of $12.50, and everyone appreciates this. It's a sacrifice I make for my friends, right? And then, or I guess I should editorialize a little bit. I have a job that requires a computer science degree to get, which means that almost no matter who I go out to dinner with, I should pay for all of us, right? So when you get a job, maybe think about that a little bit. I also tip 25%, right? One of the reasons to get a computer science degree is so that you can take your friends out to dinner and they don't have to pay for anything, right? Because they're like artists or whatever, right? Something valuable, right? Okay. So C is, which is known to be super cool and good by all of us in this classroom. They use a single slash for integer division, right? And all of my Python code always doesn't work because I can't tell I'm not writing C when I'm writing Python, right? So I don't put these 2 slashes because, not because that's a comment, because that's a C++ style comment, which I'm sworn to never write C++, right? And so I never write double slashes as a habit, right? But I also never perform naive division, right? So I'm torn every time I write Python. And the psychic damage from having to write 2 slashes and feel like I'm writing C++ drove me back into the warm, welcoming embrace of C89, the world's greatest programming language. These things both have a problem, and it's this problem. We cannot reverse either integer or naive division. We can't reverse naive division because we don't have infinite precision integers and we're going to make mathematical errors in rounding. And we can't reverse integer division because we don't have infinite precision integers and we're going to make rounding errors that we can't reverse. In both cases, there's going to be rounding occurring in the machine. We simply cannot do division in computers. It can't be done. It's impossible, and it should not be attempted. It would also be really, really cool if we could, because then we could do cryptography, right? So we fundamentally have to solve this problem in some way. This is how I think about this. For all numbers in the natural numbers, so that is the unsigned integers, not the unsigned ints. This is all of them, right? There does not exist M. Is this logically wrong? Thomas, how should I have written this? It's
Well,
there exists.
You said for all.
Yeah. Oh, this is just accidental. I just said it wrong, right? There exists a number in the reals such that there does not exist a number in the reals.
Yeah.
For which, yeah, okay, that makes sense. Okay. So there, perhaps an easier way to say this is there exists pairs of natural numbers for which division is not reversible, essentially. I wonder how I would actually write that. I'm going to write this on the board. Okay, so we know we have, I'm just going to call them mul and div. Oh, someone's on Zoom. We'll just type into the terminal. That's how I think. How long is this going to take to load? Okay. So, we have x and y, which we'll say are equal to 5 and 2. And what are we trying to show? We're trying to show that this pair is such that if we take the quotient, and I'm going to do integer division, and then we also take the remainder, it is not the case that x times the quotient equals the other value. But it should be the case because that is supposed to be the reversal of multiplication. And it in fact would be the reverse if we take x and y equals, we'll do 21 and 7. Q is x divide y, r is x% y, and it should be the case that x times q equals y. Oh, did I do something wrong? Oh, that number's too big. There we go. Y times q equals x. Okay, so if we take x and y equals 22 and 7, we take q equals x divided by y, and q is 3 in all cases, right? Then we see that this operation is not reversible. So I think, what am I saying? There exists x and, we'll call them n and m, exists n, m in math BBN such that n divided by m times m does not equal, oh, I switched back to code. See, I did not equal. That's wrong. That's it's neck. Neck n. And that's bad. Why is that bad? Because that means every time we divide in a cryptographic algorithm, we are losing information. What is one other way to think about this? So remember I have x and y. Each of these things has a bit length. And would I store the quotient? There are 2 to the 5th equals 32 possible messages that can be stored in 5 bits. There are 2 to the 3 equals 8 possible messages that can be stored in 3 bits. There are only 4 possible messages that can be stored in 4 bits, right? So there's dramatically less information in here. The same way we need progressively bigger and more powerful computers to continue multiplying, we are losing information, and therefore fidelity or whatever, right? We're losing the ability to communicate every time we perform a division. We need some way to keep track of all the information we might be losing. Euclidean division is the solution, and the way it works is you return 2 values. This is an ingenious solution. We solved the problem of multiplications getting too big by providing an additional argument, which was the modular base. And if we went over that number, we looped around, and we kept smaller than that number no matter what. We can sort of do the opposite of that, where with a multiplication, if we give it 3 values, we can 3 input values, which there's also going to be a product that we get back, right? So we can use modular multiplication to not get too big. We can use Euclidean division, which is in a way is modular because we're computing mod, to not get too small, right? And by not getting too small, we're preventing the loss of information. We're keeping extra bits around. We're having the ability to differentiate the quotients from 5 divided by 2 and 4 divided by 2, which have the same quotient but a different remainder or a different modular value. So we're not going to switch in between using integers and floats. We're not going to switch in between how big the integers are. We're going to change how many integers we return. And I know what you're thinking. You're thinking, great, I know how to return 2 values from C. You just put a comma in the middle, right? You've all done this before. So you have a function, ret 2 things, and the things are, of course, x and y, right? And you just write this, right? That's well-formed C code, right? We can tell? Okay, you're right. You caught me. You have to put a semicolon there, and then it's well-formed, right? So then it's totally fine, right? And then we just simply return 2 things. What should we return? Probably print and false. Do you capitalize false in Python? How do you know that?
I did a data science undergrad, but we only worked in Python for 4 years.
Oh, really? They didn't make you do R?
I did R for 1 class.
One class? Which class?
Data science, but it was in the math department.
Oh, the mathematicians do love R. Okay, wait, no, hold on. Sorry, we all love R, right? Okay.
You mean the R project for statistical computing?
I do. So a lot of people try and tell me, blah, 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 R is for data scientists. Why should I have to learn that? That's false. R is actually Lisp, and it's the second oldest programming language, and it's the correct way to express most concepts. And one of those concepts is the Y Combinator, which is how recursion was invented in Alonzo Church's lambda calculus, and is arguably one of the most powerful things in the world. In fact, it was a component of the discovery of general computation 15 years before there were programming languages. More, 25. And so, like any enterprising young scholar, you can look up the Y Combinator on Wikipedia, and you'll notice that the reference solution is presented in R, because that is the modern programming language that is the best suited for emulating the ideal model of general computation, which is Alonzo Church's lambda calculus. Do not become seduced by the whisperings of Alan Turing and the fact that his model gained enormous popularity and actually proved the correctness of the lambda calculus. The lambda calculus is harder to write, more confusing, and inefficient, and that means it's better, for the same reason that C89 is better. But anyways, I have it on good authority that this is our language code here, though I could not for the life of me figure out what I'm looking at. My first semester, I taught a class called cybersecurity. I implemented all the cryptographic algorithms in R, and the students said, it doesn't actually help that we know R. We can't tell what you're doing. And I was like, what do you mean? And then I found out they learned tidyverse, right? Which it turns out is a completely different thing. But I didn't know that, right? They just said, we teach R here. I was like, great, perfect. I'm locked in, right? I love doing that stuff. But anyways, this is one of the coolest things I've ever seen in my life, right? This is R being used to do theoretical computer science, right? That's just cool. That's objectively cool. There's no way to convince me that's not cool. So don't try. Why do I write loud cheers in my slides? Like, I don't know what you're going to be happy with. Okay. Euclidean division. I already had to invent the term naive division. Integer division helpfully already has a name, right? Euclidean division it's the perfect solution to a problem. I always say, why are we always giving people's names to things? Well, the problem we're trying to solve here is that this division needs a name. So we just took a name, Euclid, and slammed it on the division, right? We could just as well call it Calvin division, right? But I'm not divisive, so that would be inappropriate. So also call it division with a remainder. I only think of it in the context of the integers. To my knowledge, it's not meaningful outside of the context of the integers. Of course, there's ways you can kind of squint at modular mathematics and realize, oh, I can do that with the reals, and you can. But perhaps you shouldn't. One of the problems I was experiencing when I started fiddling around with division is you very quickly run out of names for all of the division, right? I don't really love the Python solution of just typing / twice. That feels really weird to me, especially because that's the only form of division I use, so all of my divisions are longer lines than all of the other mathematical operations. I'm most accustomed to seeing this stylized as div, and I did use div in big div, right? That's why div had 2. It was not quite division, it was div, this sort of pseudocode operator that's around, as some people understand linguistically. But div is also, it's the first three letters of divide, right? So all of these various other operations. I usually associate this with set minus. So if I take the set of ABC backslash the set of A, I get BC back, which stands for British Columbia, right? So that's actually how Canada was invented. And then we also have percent, which I always pronounce as percent, even though it's mod. I don't really know what to do about that. And that, to me, really looks like percentage is a ratio, right? So it seems odd to me to use the remainder. But anyways, it works, and it's a key on your keyboard. But one of the things I noticed is that there's like a lot of remaining keys on my keyboard that aren't used, and I was a little bit surprised by that. But, for example, if we just run down this list here, most of these are arithmetic operations, right? So we use then for logical negation and not equals. We don't use at for anything, but it would probably be pretty weird to use that for Euclidean division. I don't think we use octethorpe for anything, do we? I think they're called elites now. Dollar sign, I use percent, that's one to use. We use the caret for XOR most commonly, ampersand for logical or bitwise OR, multiplication, right? So many of these are already taken, and I guess it would perhaps seem odd to use the dollar sign or the at sign for Euclidean division. I also believe some of these are regional. Has anyone ever been to another country? You said something about Montreal once. Do they have dollar signs on the keyboards there?
I can check.
It's the Canadian dollar.
Yeah, we have Canadian dollar, so it would actually just multiply the number by about 0.75.
That'd be weird if you like cross an international border, all of a sudden all of your Euclidean divisions.
They do have a dollar sign on their keyboard. They do not have curly braces.
They don't have curly braces. Okay, so curly braces are used a lot more than dollar signs in most codecs.
And they have a caret, but only in the context of adding it to a letter. They don't have it like a standalone caret key.
Wow, it's like they don't care at all. Okay. It's been a long week. You'll know, so I keep trying to start engineering schools, right? I've actually been trying to start the same one continuously for a year. Anyways, I had to convince a very large number of humanities professors they wanted to teach at an engineering school this week. And as a result, my brain turned to jelly and started dribbling out of my ears. I haven't even been able to play Monster Hunter Wilds, my one true calling. So some of you have, I'm going to stop making fun of Python. In Python, we can implement Euclidean division using the built-in operators. One thing I want to point out here, starting with the finite lecture, I'm trying to be very, very specific about what types of things we're putting into and taking out of these algorithms. There is nothing particularly in this code here that's compelling you to only provide integers into x and y, right? Python's not enforcing that. And you'll say, or some people will say, oh, in C you do say what type the things are, so you have to provide them. That's wrong, right? What you're really telling the compiler is these things are probably something that looks a lot like an integer, and you get to decide what the maximum size of that integer is, and I'll just trust you, which is in a way worse than just not saying what it is in Python, right? Which is why we should all learn Fortran, which I was writing a bit of this week, which is quite enjoyable. Anyone written modern Fortran, like the 1990 and later? Anyway, it looks quite fast. I'm going to fiddle around with it more. We'll see if it works its way into this class, right? But there was just a recent Fortran standard that came out, maybe like Fortran 23 or something, and people are using it for the really fast ML stuff, because it's a language that parallelizes well. So that's interesting. I did not think I was going to look up what is the most popular scientific programming language in 2025, and Fortran beat out like Julia, MATLAB, and Python. But anyways, that's what's going on. So anyways, in Fortran, you would actually have to specify this. Fortran is strongly and statically typed. C is not, and Python is not typed at all. But it is always of importance to me to point out that Python mod is modulo, it is not remainder. It is forcing those values to be positive, and that is distinct performance from C, as we remember from Enigma, right? I spent 80% of my dev time on Enigma not remembering that. Some of you have been streaming long division by me. It's on mega.mz, the website for cybercrime, right? And I thought I did some cybercrimes. I tried to post it on SoundCloud. Turns out that I don't actually think it's against the law, but SoundCloud thinks it is, right? And, so anyways, I'll be using these words interchangeably. I am much more comfortable with dividend and divisor, and that is unfortunate because they sound the same. I don't know that I've ever remembered whether the numerator or the denominator is the numerator or the denominator. That's outside of my skill set, right? And then I tend to prefer quotient to fraction or ratio, so I'm going to mostly be using the first line. Remainder is modulo over the naturals, and I only work with naturals, and so that's why none of my C code worked, because I'd never worked with a non-natural number before. This is the thing that I showed earlier in Python. Right, we all remember Python. Maybe named after Monty Python, unironically? Does that sound true? Yeah. I would have kept that to myself, right? We can force values into being the naturals. This one matters. I haven't introduced too much the terminology like invariants, things that do not change about program, but we can assert at all points in time. If we take a modulo operation, the result of that operation is smaller than the second operand. And it is less than or equal to the first operand, assuming they're positive. If they're negative, it changes, right? And so we can see that quite simply. 17 mod 4 is less than or equal to 4. 17 mod 18 is less than or equal to 18. And it is also less than or equal to 17, right? And it is strictly less than the right-hand side, and it is less than or equal to the left-hand side, so this is a shrinking operation. Multiplication over the integers always makes them bigger. Modulo over the integers always makes them smaller. That's very useful. That's how we keep our numbers finite. There are also minimums that apply over this. Why might I care about a minimum? I'm about to take a potentially very large number, a potentially 4,096-bit number, and I'm going to raise that power to itself roughly a gazillion times, right? I'm going to find some enormous prime numbers. So I'm going to be doing this a lot, right? It could be the case 4 is congruent. I'm learning to say congruent. Thank you. The undergrads have been cooking me. They reported me to Professor Erin McNicholas. Do you know her?
Oh, yeah.
Yeah. No, so so I was trying to pitch the engineering school. I walk into this room with like a religious studies professor, and Colin Starr's there. He's our other number theorist. And he's like, I hear you've been saying equivalent instead of congruence. I was like, what's going on here? So I've completely started a scandal. I didn't know anyone used words correctly. So anyways, thank you, because the undergrads were just letting me clown myself, right?
Yeah.
And you're an adult, thank you.
Well, yeah, I mean, it's equivalent. It's equivalent.
Yeah, it's cool. Yeah, it's
Right.
right. Yeah.
I mean, I don't know. I feel like we're both right.
Yeah. What I said is, we are just as precise, but I am less specific. So I think I was getting made fun of for not being specific, which is a problem because I've been referring to the assignments in this class as specifications, right? So I really don't have a leg to stand on there. Anyways, there are other numbers than 17 which are congruent to 1 mod 4, and not all of them are smaller. Here's a fun one, 21. What does this mean? This means that when I find a decryptor that corresponds to some encryptor, I really want that to be the smallest decryptor, because there are an infinite number of possible decryptors. Probably. I didn't write a proof. No, there has to be, because you can just do E times D again, right? So I want the smallest possible decryptor, and I want the smallest possible decryptor because there's no guarantee that I'm getting a finite-sized decryptor, because there's also an infinite number of infinite-sized eligible decryptors. And even the second smallest decryptor is absolutely enormous, right? It at minimally doubles my end-to-end encryption time, and it dramatically increases my decryption cost, because the encryption cost is distributed onto the person encrypting, right? So it is valuable to me that I am getting the minimums back, right? The smallest possible positive value. I really want these smallest possible values. And some of the proofs and things throughout this class at various points in time, we've assumed we've gotten the minimum value back, and oftentimes you're allowed to do that. We are going to guarantee ourselves the minimum value back by just using naive and integer and Euclidean division. We like minimums. So what are the takeaways here? Remainders are small and positive, right? It's what's left. We get to keep using the integers. In my RSA implementation, I use the natural numbers everywhere except within the Euclidean components. And then I went back and I took out the integers, and the code got dramatically more complex. I think this is probably a good thing because I wanted the complexity to be inside the Euclidean operations rather than in my big operations, right? So I left the complexity there. It was 20 instead of 7 lines of code in exchange for not having to make any further changes to 49060, right? So that made sense to me from a design perspective. But we get to minimally keep using the integers, which are way easier to use than everything else. You all probably remember when I was introducing SHA 256, we had this sort of starting hash values, which was the, what was it? It was the fractional components of the square roots of the first n primes, right? And I tried to calculate those without using floating point values, and then I gave up and used floating point values. And you know how much I love floating point values, right? And so that pained me greatly, right? It burdened my consciousness and my psyche, and I still haven't figured out how to do that without them. I understand every single step of the operation cognitively, right? I cannot get the code to work. And so I argue this is a great value for being able to stick to the integers. The floats are unstable, and they don't have any of the properties we want of reversibility, right? And we've already implemented the integers, right? So not having to deal with things that aren't integers is very good. In general, we'd probably like to work with the unsigned integers, but whatever. That's Euclidean division. I was sure I fixed that one. Okay, the Euclidean algorithm, which has no m in it because m is a secret, and we're not disclosing the secret, right? It's m to the ed. You're not supposed to know that, so there's no m, right? Okay, it is an algorithm with algorithm in the name. Who remembers the secure hash algorithm? Remember I walked in here, I said this is the best algorithm. Why is the best algorithm? Has algorithm in the name. That's a bit of an exaggeration, right? We actually call it SHA 256. We don't say algorithm. The Euclidean algorithm, we call the Euclidean algorithm. That means it's an even better algorithm. This is our best algorithm so far. This is our current winning algorithm. I've also seen it called Euclid's algorithm. I talked to recurring character Aaron McNicholas. Aaron McNicholas refers to this as Euclid's algorithm and also teaches a history of math class, so that seems good to me. Keeping with my consistent style guide, which is I try to go out of my way to avoid referring to things by people's names, right, which is the recommendation of the society formerly known as the Audubon Society that changed their name because they were named after a person. They named birds, right? I name algorithms. The name for this algorithm is the GCD algorithm. So it is what it does, right? I'm going to refer to it as Euclidean because Professor Aaron McNicholas does it, and that's ground truth. Given two values, the Euclidean algorithm finds the greatest common denominator. That's interesting, right? Because we started by doing Euclidean division, which was just dividing things. But okay, denominator that's one of the two things that's either the denominator or the numerator, right? I don't remember which one it is, but did you know?
Pretty sure the numerator's on the top, right?
I think it's on the top, so that would make it the dividend, not the divisor.
I grew up in North Dakota, so like ND, so I just like think of N over E.
North Dakota. I'm trying to remember the capital of North Dakota. You have to say spoiler alert. I've been robbed. I'm so offended right now. Okay. Anyways, Bismarck. I'm gonna try and spell Bismarck to make up for it. Bismarck. Okay. I'll give myself partial credit. And now all of the rest of you have to come up with one North Dakota fact by the time we get back from dinner. Okay? You're not allowed to Google, but you are allowed to think. Okay. Wow, I'm so distracted tonight. How's everyone doing? Y'all doing okay? All right. I hope you're having a nice week. I stopped sleeping like when I got home from class last night. Okay. Whatever. The way I've thought about this is, at some point in the past, there wasn't division and someone had to invent it, right? This algorithm describes division without performing any divisions, right? We used modular exponentiation to turn multiplication into exponentiation, right? We did it modularly, you don't have to, right? So we've invented exponentiation in this class, and we've shown there's actually reasons to do it that way. You would never do division with repeated subtraction, right? And you would never do multiplication, probably with repeated addition either. But if you're just writing down how this stuff could happen, right? I don't think Euclid or the ancient Greeks were that worried about the time, complexity, cost of algorithms in 2025, which they should have been, but they weren't. So they just wrote things down with repeated subtraction. Please go. I'm going to step through this example, and then I'm going to go eat dinner. They told me they'd have vegan pizza by 7:30. We'll see what happens. We're going to have an increasingly chaotic class as my blood sugar continues to change. I'm trying to think if I can come up with something funny about greatest common, right? Like, there's the common people, right? The salt of the earth folks. And they are in some way great, but I don't have anything. We're going to take 1071 and 462. What's the greatest common denominator of those two values? Does anyone see it?
What was the question?
Do you know what the greatest common denominator is of those two values? Do you have it?
One.
You think so? You think 3? There's a multiple of 3. Okay, so we're going to take the largest value. Or, well, okay. The takeaway there, these are very small numbers, right? 1071 is the bigger number, and that thing is just barely 11 bits, right? It's just squeaking across the line. 462 is just barely 10, right? No, it's 9. Not very many bits, right? I have no idea, right? Prime factorization is so hard, right? And so, I don't know, let's figure it out. It turns out there's a very easy way to do this, and in fact, mentally, if I had to do this, I would just run the algorithm. It's the only way I know to actually do these operations, right? So, we're going to take the larger value. Which was the larger value? Does everyone remember? 1071, right? Yeah, 1071. Great number, good year. Think maybe there was a schism between the Orthodox and Roman Church at that time. It's right around then, maybe 1080, something like that. I don't know how good they were at telling what year it was then, so maybe it's wrong. I'm going to subtract the smaller value from the larger value until the larger value is no longer larger. So while x is bigger than y, I take y's out of x. So if I have 1071 and 462, I'm going to subtract 462 from 1071. Am I going to try and do that math mentally? Of course I am. That's what I do for fun. So we have 62 subtracted from 71, which gives us 9. So we have 9 left. And then we're going to take 400 from 1,000. So we're going to have 609 left. We're going to do that again. And we're going to get something around like 159 or something. That doesn't sound right. Anyways, we're going to keep doing that over and over again. I'm not going to do them all in front of you mentally. Would it be more fun? Do you want to watch me do mental math? My students have started sending me arithmetic problems. I'm like, no, I can always divide 63 by 7 while you're not there. Like, I don't need... Okay, fine. What am I doing? It's not an equivalence relation. I'm going to mute Discord because I have to look, or display capture because I have to look at messages and I don't know what's going to come up here. No, that's the wrong message. Okay. There's Sam. Okay. All right. Okay, student sent me this. We'll turn this back on. So I think people have the impression that I do mental math for fun, like when I'm not in class, or like I go home and I'm like, wow, those 5 minutes we spent doing monkey type were like the highlight of my day. So I've been getting sent increasingly silly websites, right? And anyways, here's one of them. So you all get to watch me for 120 seconds. Oh no, that one's hard. It's 480 minus 16, which is... Wait, am I doing it wrong?
64.
Oh, it's 64? You're not supposed to help, I'm supposed to struggle.
We're gonna make you do one of those things that they have with little kids and they flash
Oh,
the
no,
numbers
minus
on the screen and the kids are doing like hand gestures and like adding 50 numbers together.
Okay, so it's less than this, right? By 10. 87. Oh no. Oh, why am I so bad at things? I like that one. 47. 53 plus 58. Whoa, that's I like that one. 82, 3, 5. They're easier if you do them digit-wise. So that's. Oh, I'm so tired. 4 times 87. Come on. So that's 320 plus 28. Oh, I like that one. What? No, I'm wrong. Wait. Oh, I'm so bad. Okay. This should be easy, right? 6, 30, wait, it's 70?
Is that right?
It's
Oh, wait, no.
it's 7 times what's 36? Oh, 4. There we go. Oh, I thought that was division, and I was like, this is only integers. Okay. Anyways, thank you. I gave them the midterm today, and I did this nonstop for 90 minutes. My high score is 31. And then I realized that I had actually a job that I should have been doing for those 90 minutes. I regret nothing. But I did say, here's what I maintained, and I think this is true. It is unfair that those values were represented in decimal, because I'm primarily trained in other number systems, right? I think it would have been trivial in base 16, right? I think I could have gotten to 40. Okay. So we have a terminating operation. We reveal now that we are sort of working with Python as pseudocode, not actionable Python. So I don't actually, so this is supposed to be in a for loop, right? I don't really have a for loop, so I just jammed an exit in there. Exit and quit are co-aliases, right? But under what conditions do I exit? I exit if one of the values is 0. Specifically the smaller of the two values. Now I was always sorting things with min-max, right? So I just have to check to see that the min value is 0. Why is that? Well, at some point in time, when I divide or subtract, there's not going to be any remainder. So I don't have to worry about continuing to do the divisions anymore. So this is a sort of building naturally towards a while loop construction. And here it is. Speaking of monkey type, I actually just tried to type Euclidean algorithm, and it's different on all of these slides. So this is the EA, the effective altruism, and I take A and B. Oh, really? No laughs for effective altruism. Anyone love Sam Bankman-Fried?
The name is right. No love for him.
No love for him. This is a crypto class. Okay.
Doesn't mean we love crypto bros.
I think so. Okay. What are we doing? Okay, right. Okay, so, well, the minimum is non-zero. Order them, maximum first. Perform the iterative subtractions. At the end, return the max. That is how you compute the greatest common denominator using Euclidean division. Why do I say Euclidean division? There's no divisions here. We do this purely with subtraction, right? So we're able to perform divisions with subtraction only. And that's really cool. I bet it would be a lot cooler if we used mod, which it is. Look how many lines I saved, right? Spoke a little bit about how long you should expect things to take, right? We don't need to think about complexity too much, but that's a while loop inside of a while loop, and this one is a single nested while loop. So this should be exponentially faster. we're just calculating the modulo using subtractions, right? Why are we doing this? I want to show this for historic reasons. I want to show that you can build division out of things that aren't division if you have to. Why is that of particular academic interest to me? I've been spending this whole semester trying to think about where the electrons are going inside the transistors, and I can't figure out how to do division with a circuit. I can't figure out how to solder it, right? So in a pinch, if I had to do this, I could write, or I could build a circuit that could do this operation, and I can't build one that can do this operation. I don't know how to write modulo in a hardware design language. I can't figure out how to do it, right? And I looked up how to do it. I think I said this, and I still don't know how to do it, right? It's that much worse. Big div was way harder than everything else, right? So I just don't know what to do, right? So in a pinch, you just use Euclidean division, right? This is how modulo was invented. This is how remainder was invented. This is how division was invented. We got all three of the operations at the same time. They're largely equivalent to each other. You can also do this recursively. Does everyone love recursion? Are we all recursion appreciators in here? Yeah? Yeah? Woo, okay. All right. Didn't both of you say you did big div iteratively? I'm revoking your recursion license. No, go.
Like doing recursion when we have to work with buffers. Or
I mean,
like pointers.
I was gonna say, I like recursion, it's just, I like segmentation calls, but my operating system doesn't like segmentation.
It is true, I do love a segmentation call, right? Sometimes I just write myself a little segmentation call as a treat before breakfast, right? Like you're there burning the coffee, you're like, should give the operating system the fear of God, right? And just, you can just divide by 0 too, it's quite easy, right? So anyways, I found this much conceptually easier. One of the things we always say is that this is faster because it's one line of code. That's how you tell, right? So, okay. You can also write this with helper functions, as I do here. And I do that because I don't love putting all these min-maxes everywhere. So I wrote a recursive effective altruism using a helper where I just sort max and min. And then I always just reorder the min and max inside the helper as follows. And then I return the non-zero element when one of them is 0. So this isn't too bad. This is just a couple lines of code. $1071 and 462, right? It's 21. So I think that's pretty cool. And on that note, it is blood sugar o'clock. I'll see you all soon. And I'll be even more cheerful than my normal cheerful self.
Was the pizza you mentioned supposed to be free, or?
funny as possible.
You started at Jane Street?
He started at Jane Street.
Oh.
His parents were like academics, and he then
that
like
checks
created
out.
like the world's funniest Ponzi scheme.
Yeah.
And then Sam Altman is like a serial failed entrepreneur who has finally succeeded with OpenAI.
Huh. Weird.
Who is accidentally feuding with some of the worst people out there.
Yeah, I mean, that seems easy to do. I feel like most of us have feuds with terrible people right now.
But you get the sense that he's doing it purely accidentally, like.
Yeah, he doesn't seem to know they're terrible.
Right.
I watched him.
I think that's giving him the benefit of the doubt. He's probably been terrible. No, probably. But we don't know enough about him to know that for sure.
Well, he's just impossible to care about. Like, he's like an NPC, right? But, or sorry, I'm not allowed to call other people NPCs because that's right-wing coded and I'm not being partisan. Okay. What I meant to see is a non-player character. Okay, so, okay, I'll say one unmotivated remark specifically about Sam Altman. The happiest I have been as an educator under the current regime is 36 hours before DeepSeek dropped, Sam Altman was in the White House talking about how they were definitely going to be ahead forever thanks personally to President Trump. And I'm assuming the Chinese were literally watching that press conference and then just released DeepSeek, which well and truly put OpenAI in the ground, and they've not gotten back out of it, right? And why do I say that as an educator, right? I'm pretty sure I'm doing something of value with my life. Like, it's up to you, all right? But like, I looked at how OpenAI was going to have faster AI, and they said, we're going to keep buying more GPUs than other people. And I was like, that's not a strategy for research, right? Having more money than other people is like, that's like a weird way to solve problems. Okay, right? Yeah, and one of the problems is, of course, there can always be someone with more money than you, right? Yeah, and I was like, are we even sure they're like doing anything that makes sense on the GPUs? And like, there's no real evidence they are, right? I remember talking to my colleague Rachel Brown, who's teaching computer vision, right? And I have a more extreme position than Rachel Brown, who actually understands the research, right? But the Google DeepMind team that did AlphaGo and AlphaFold and all of those ones, right? A lot of people are like really excited by the research lines. And I was like, I think if I had that much compute power, I could also solve every problem, right? Like, and what Rachel points out, and this is a good point, was like, oh, well, they had some insights. I was like, I know, but like the level of insight you have to make something work when you have Google's compute power versus the level of insight you have to use to get something to work when you have my level of compute power, are like, those things are not comparable. I've maintained these like completely free and open source, 0 monthly cost tech stacks for years now. And like, I'm not gonna say that's like more impressive than OpenAI or something, right? But like, I don't know, it'd be interesting to see them do something with any resource constraints at all, right? Like the White House has never called me up and be like, how much money do you need to teach the best cryptography class? Like that's never happened, right? This would be a very different class, right? First of all, we'd only be GPU programming. Like on the first day of class, I would be like, here's, what's the new NVIDIA, like there were 4080s for a while? I don't know, I don't follow graphics cards.
5090 at this point?
Yeah, they just keep adding numbers, right? Like here's your 6010, right? Because of course they're all base 16, right? And so like, here's your 60A graphics card, and we're only GPU programming from now on. We're learning CUDA C++, and I'm gonna bring in guest speakers from different research facilities. And then, okay, one last thing. I look up MIT OpenCourseWare, because I was like, I take classes at MIT for free in my downtime. And I was following along on this systems engineering class, and lecture number 13 was Meet the US Secretary of Energy. And I was like, come on, like, I don't have those resources. Like, I'm not MIT, right? This is cheating. This is, like, how do you even tell if you're doing a good job teaching if, the US Secretary of Energy shows up to your class to explain systems engineering to your students? Like, you'll never know which one of you taught them. Okay. That's what I think about Sam Altman. I think he should run his entire OpenAI framework inside GitHub Action workflows. Okay. Speaking of effective altruism, which is the SBF.
Not Electronic Arts.
Oh yeah, Electronic Arts. Any gamers? That's a trick. Put your hands down. Okay. We're students.
Whenever whenever I see the EA, I just hear the the sound. The like EA Sports, but they edit it so every sound is an E.
I'm not familiar with that, but I'm happy for you.
Yeah.
I'm a known. You have a soundboard.
I mean, I have a folder in my doc that's just called sounds, and it has like maybe 100 sounds. Some of them are duplicates of each other. I've got a couple explosions.
I sure hope like this is picking up for our remote guests. We're fine. Like,
some good stuff.
yeah, Liv Moss. Liv Moss.
Anyways, back to the topic.
Yeah, sure. Yeah, back to the topic, right? So here's a quick recursive function. I think this is getting pretty close to an example of why you should write recursion, right? If you can write recursion like this, what were you doing in your loop, right? That if is presumably the loop terminator, but this is the same number of lines of code. And I would argue it's more readable because line 3 is self-documenting because it's documented with the function name. So the Euclidean algorithm of A and B is the Euclidean algorithm of B and A mod B unless B is 0. That makes sense. That's the invariant. That's the thing we're satisfying, right? Here's the example. Let's plug in the print statements. Surely I have.
But I thought there was 2 parts of the Euclid. I thought you get 2 things back.
There's 2 parts of Euclidean division.
But this is not that.
This is the Euclidean algorithm, which uses Euclidean division to compute the GCD.
Gotcha.
And specifically, it's using the remainder component, and it's throwing out the other part. Now, you asked the correct question that you were supposed to realize you should ask, so keep that in mind. Okay. So right now we are throwing out all of our quotients. I hope we don't need those later. That would be so embarrassing if we were throwing them out and we need them later. We'd probably have to do like a ton of overhead to capture all of those quotients and find some way to log them. We might have to use them for something like computing a multiplicative modular inverse, right? Like, who's to say what we would do with those quotients? But we're not that far yet, so we haven't thought about it, right? So instead, we've only thought about taking the effective altruism of A and B. And I plugged in a little print statement here. I thought this was a reasonable way to do things. And we can EA 1071. I guess this is also recursive, but it's not written with a lambda. What is happening here? So I stood before you, and I remember distinctly saying 1071 minus 462 was like 600 something, right? 609. And then I said, well, if I subtract 462 from that, I'm going to get a little bit less than 150. This is that 150. What does that represent? The remainder of 1071 when divided by 462 is 147. That is the second part of the Euclidean division. It is the mod, it is the remainder. It doesn't matter what we call it. What am I going to do with that 147? Well, that 147 and 462 have the same greatest common denominator as 1071 and 462. Why is that? Well, I divided out everything they don't have in common, right? So 1071 and 174 are in some way divisible by some of the same values. Not all of the same values, but some of the same values. And in particular, they're both divisible by 21, right? Why are they both divisible by 21? Well, because 462 is also divisible by 21, which means that when I'm subtracting 462 from 1071, I'm taking a bunch of 21s away all at the same time. Now, while I'm doing that, I don't know that I'm taking the 21s away, because I haven't found the 21 yet, right? So I'm going to take away a bunch of multiples of the greatest common denominator, because both of them are a multiple of the greatest common denominator. I can think of this in terms of 1071 is something times 21, and 462 is something times 21. And I get 147 back, which is 7 times 21, right? So I have 462, and now I'm going to divide 462 by 147. I'm going to throw out the quotient, which is definitely not going to come back and bite me later. Wink. Haha. Wouldn't that be suspicious? Okay, it'd be odd if we spent a bunch of time talking about how Euclidean division returns two values and then only used one of them without discussing it, right? So it's a good thing we didn't do that. Anyways, so we take 462 divided by 147. 147 times 3 is about 450, right? So we're not going to have that big of a number left. You can see that's 12 more than 450, and then there's 3 3s that come from 47. So we have 12 plus 9. That gives us the 21 back. I can do that one mentally, right? It's easier while I'm looking at the answer. But so then I take 147 and I divide it by 21. As specified, 21 is a seventh the size of 147, right? So I get a 0 remainder. And that means that 21 can be multiplied by something to get 1071, and 21 can be multiplied by something to get to 462. I wonder if there's some way to figure out what we multiply it by to get that 462, right, so, okay. So that is the Euclidean algorithm, and you're welcome to test this. Because I am living in the future, all the way up here at the front of the classroom, I'm living in the year 2025. It's not at all like you living in ancient Greece, right? So I can do division, and I even just used naive division. I treated myself to a little bit of float division, right? Because I didn't want you to just believe me that those things are evenly divided. Now, of course, you should still not believe me, because you should not believe that Python conducted those divisions correctly, because I've shown you division errors in Python in this class, right? But not to worry, you can verify that yourself. 462 is 420, which is 20 times 21, plus 21, right? No, plus 21 twice, because we go from 420 to 441 to 462, so we can do that one mentally. And we have already demonstrated that 462 plus 462 plus 147, which is 7 times 21, is equal to 1071. So you don't have to believe me, you don't have to trust Python. I would not trust Python either. It constantly lies to me. The other day, it claimed it was the third version of a programming language, which is not true. Python 1 and 2 are the same programming language, right? So it's actually Python 2. Anyways, that's what's going on. So I asked GitHub Copilot for this code before I made these slides, and I knew what I knew what the Euclidean algorithm was at the time, and I had actually, not until teaching it this term, ever seen it recursively, which separately means I did not understand it, because I looked at the recursive version and didn't realize it was the same algorithm. So that was a little fun takeaway for me when I got to this point in the slides, because my plan was, when I was putting these slides together, I was like, now that we've taught the extended algorithm, we will implement it in Python, and then I checked the answer key, and it had already been written by an AI, which correctly guessed that I wished I knew number theory. Okay. Let's press one more button. There we go. I think it's well known at this point in time that Wikipedia is the only good website, other than my website, of course, which realistically should be part of Wikipedia. It's, I could implement my website as a wiki. That sounds fun, right? Okay. I'll think about that. That's one of my worst ideas. Some people like to visualize this stuff geometrically, right? So on the left-hand side of your screen, simply banish from your mind the fact that you know that I have a 1080p monitor, and so that this monitor is exactly 1080 pixels high. And just pretend that thing is exactly 1071 pixels high, which is a little bit difficult to believe because there'd only be 9 pixels left, and I can see at least 10, right? So pretend those are pixels. That's what I'm doing, right? So, okay, we take something that is 1071 pixels by 462 pixels, right? And we can simulate these divisions just by filling it with squares, right? So we take 462 by 462 squares, then we take 147 by 147 squares, and then we take a series of 21 by 21 squares, I think, and when we run out of the 21 by 21 squares, we see that there's no area left, so we know that 21 would evenly divide up the whole thing, and we could tile this whole thing with squares of size 21. Do you like the geometry? Is that okay? Yeah. Any of you big fans of JavaScript? Yeah. You could write this, right? That might be a fun little task, right? It's not that bad. When I was teaching CS 151 this term, I implemented the Python solutions in JavaScript. And my coworker, Professor Jed Rumbold, said, you can't do that, you're giving the students the answer. And I said, if they can translate JavaScript to Python in a 100-level class, they deserve an A. That's what I said. I don't know if we're still getting along. I'll report back to you. Ooh, I wonder what the extended Euclidean algorithm was. I don't know that there's any clever hints that have been sprinkled throughout the class that we can use to infer what the extended Euclidean algorithm will solve. But tip of the hat to extended Euclid. That's an algorithm with algorithm in the name. And that's my favorite kind of algorithm. Also called the extended GCD algorithm. So I've only seen this as extended Euclidean. I was subconsciously also thinking of it as the extended GCD algorithm. That's an odd thing to say because the extensions don't apply to the GCD part, right? They specifically apply to Euclidean division, which isn't really referred to in any other way. But it's important to try and maintain consistency with naming standards, right? So, how bad is this? That's what we should ask ourselves now, because it's time to solve this problem. It's time to rip the Band-Aid off. And this is a loop. D increases by 1 each time. And I will potentially keep getting unique values for the test statement for the while loop until such a time as D grows at least as large as lambda. Lambda is Carmichael's totient function of 2 big primes. How big are those primes? Well, they're big enough to get a 4096-bit key, which means lambda is potentially, probably not, it's probably smaller, potentially size 4096 bits, which means I could have to loop 2 to the 4096 times. An astute student will notice that that is many, many times bigger than Google, right? Google is 10 to the 100th, which is equivalent to 2 to the 30th, which is a lot smaller than this. That can't be right. Something like that. No, 2 to the 300th, right, which is much smaller than this. So this is many Googles. So we previously did the calculation about how long it would take to count to a Google in Python. It's forever, right? It is a much, much faster forever in C, but it is still a forever. It is a finite amount of time, but it's a very large finite amount of time. So this is unusable on our key size. I think, to me, it looks like this stops working at around 8 to 16-bit key size, and I'm sure it's computer dependent, right? Because it's pretty easy to make C go 100 times faster than Python, which of course cooks how big your estimations are, right? There are, in fact, the hot startups coming out of Silicon Valley that write code that is 100 times faster, but none of them write code that is infinity times faster. Right? I thought it would be interesting to show how many times this loop would run, and I know that you all love the decimal number system because you went to public school in the United States. Can I hear it for public schools in the United States? Yeah, let's put those hands together. Yeah, then you go to private school? That's right, keep that to yourself. Okay, so I went to private elementary school. Oh, we're currently in a private school. You all went to private school. Our student profile is consistent with public schools. Anyways, there's quite a few digits here, right? Now I'd like to point out, and you are not all required to do the undergraduate midterm, if I expressed this in base 64, it would in fact be shorter. It would be like 30% shorter. So that would make this basically a reasonable length, right? Oh, look, it's still going.
What if it was in base 85?
That would be almost exactly the same length as base 64, right? Did you figure out what the nicety of base 85 was by just thinking about it?
I didn't read the thing. I had other stuff going on.
It made sense to me almost immediately for the following reason. Base 64 means you're looking at chunks of 6 bits. And the problem is 6-bit chunks are aligned with 8-bit chunks on a 24-bit boundary. An unbelievably annoying boundary to be aligned on, right? What problem does base 85 solve? Well, we know it's bigger than 64, so where's the next place it lines up? Base 64 uses 4 characters for 3 bytes.
Base 85 uses 5 characters for 4 bytes. But 4 bytes is the useful size. It's the 32-bit size that we use in SHA-256. So all of the stuff works with 32 bits. So base 85 is really, really nice because it just so happens 2 to the 85 to the 5th is exactly big enough to store 2 to the 32nd. It is the minimal value such that it is true. And there just so happens to be 85 printing characters. So base 85 has this like uncommonly good insight. Now, of course, it instantly breaks in every practical sense because some of those 85 characters are quotes, which means you can't use it anywhere, right? But it's used internally inside Git, PostScript, and PDF, and it's just that much better, right? But what I noticed, and the reason I gave base 64 for the practice midterm and base 85 for the real midterm, is the students were getting absolutely fried by having to deal with 24-bit chunks because they'd never dealt with anything that had a prime factorization containing 3 before. Think about how you have to implement endianness on 24 bits. It's awful, right? The only way you can figure out what to do is you have to test a bunch of stuff really quick, right? So I gave them the 24 bits on the practice midterm, and I said, base 85, and they're like, oh, base 85 is not powerful, oh, I'm so sad, I'm so sorry. It's like, well, first of all, you don't have to use a string, you just add a numerical value to get the ASCII character, so that's easier. And then secondly, you get to work with 32-bit chunks. And so actually, I wrote this code, now I can't figure out why we didn't use base 85 for everything. So I was chatting, and I was thinking, Willamette University should start maintaining the base 85 binary in APD for the Ubuntu package manager, right? Because no one else is doing it, and I'm looking for things to do with my time, right? So I think we're going to have to do it in Rust, probably, to be cool. But well, that reminds me of something. The next Rust PDX has been announced. So when is it? What are we doing April 10th? Any fifth class? It'd be this one. Oh, it was the day we were going to do blockchain. Anyways, think about it. We can go meet the Rust people. Okay. So, all right, you caught me. Secretly, the whole time we should have been keeping track of the quotients. I know. I was surprised too. I was so used to division only having one return value, right? I remember my kindergarten teacher programming me to do division, not returning a tuple at all, just returning a numerical value. Such sloppy coding, right? Very poor documentation, right? I still don't know if it was naive or integer division. All of the use cases were ambiguous, right? So I'll have to reach out to my kindergarten teacher about this and maybe submit some pull requests to that curriculum, right? But we can solve the problem now. We're going to introduce the normal expression, Bezos' identity, who's named after a business magnate from Florida. A lot of people don't know that, but Bezos is in Florida now. Pursuant to name discourse, this was accepted as a lemma by something in the 300s Common Era in China. So it is in fact named after someone that had discovered it 1,400 years after someone that perceived it as trivial. And that is the level of success I aspire to, right? I was like, what if we take all of the really hard things that like electrical engineers and mathematicians discovered in 1939 before computers were invented, and were smart enough to implement them in Python, the language that already has all of the things in it. Like, yeah. At least one of the undergraduate students said, I included base64.h in my C file, and then I found the base64 assignment was very easy, and I was like, good job, why'd you bother writing that code, right? Like, did you learn something? Another student used the system interface to call the system function base64 from inside a C code, and I was like, you don't actually have to compile that, you can just rename it, right? Okay. I'm fine, and I'm not mad at all. Okay, so, what's this monstrosity? Y'all heard of the GCD before? We calculated it using electronic arts, right? Actually, that is true. That's unironically true. That is how we calculated it. Okay, fair enough. Man, why doesn't EA make Linux packages? That'd be cool, right? Like, we make Electronic Arts, we got the base 85 package, we got the base 58 package, we got base 32.
Apt-get install FIFA 2016.
I don't think we like FIFA either. Okay, so EA FIFA is just too bad.
Apt-get install Madden 2025.
Sure.
It's Madden.
Do they have one for like indoor track cycling? That seems like we should release a package for indoor track cycling on APT for Ubuntu.
I can't wait to play a very detailed simulation game about cycling like a criteria.
That'd be fun. Yeah, it sounds fun, so it would be. Do you all know what linear combinations are?
Yeah.
Yes, you do. You're in Data 505 where you take linear combinations of feature vectors. They're called coefficients, right? Okay, so numbers have features, and those features are prime factors. We can express every number as a linear combination of its prime factors. Wait, that's actually true. That is true. Okay, that's good. Okay. That's less true than I wanted it to be, but don't look at it too closely and you'll realize it's basically fine, right? So here is an example of a linear combination. We have some GCD, it's 21. We have some numerical A value, it's 1071. And we have some numerical B value, which is 462, right? 462 is that 21 squared? It can't be, right? Anyways, it can't be because it ends in 2. It's 22 times 21, perhaps. Okay, so, and we have the GCD. And what we realize is because we were performing a series of repeated subtractions, that necessarily what's going on here is there is some value by which we can multiply A, and some value by which we can multiply B. Then when we add them together, we get the GCD. So, every way we combine A and B, two values that share a GCD, we are just getting various multiples of the GCD. What does this mean? Well, really it means that the smallest value I can describe with the combination of these two values, the most precision I have, is multiples of 21. Remember when we were doing hashing and we multiplied things by 15 and then divided them by 20 and we could only get multiples of 5? That's the same thing that's going on here. We can multiply and subtract A and B, but no matter what, we can't get numbers that are smaller than the precision of 21. We can express any multiples of 21, but we can't express the idea of 19 by combining 1071 and 462. There's nothing I can multiply them by. Now, I can multiply them by non-integers, right? But one thing to point out, A and B are integers. So are X and Y. This means that A and B are allowed to be positive and negative. Some of you may have realized there's no positive number I can multiply by 1071 and add it to another positive number multiplied by 462 to get 21. That's correct. Good job. I commend you on your spot-on analysis, right? So we're going to have some positive numbers and we're going to have some negative numbers, right? Here's another way to think about this. 1071 divided by 462 is 140, no, is 2? Integer 2, right? And so if I put a 2 here, a negative 2 here, I'm going to get 147 back, which is a multiple of 21, right? If I double both of those, I'm going to get what number over here? I'm going to get 294, which is 147 times 2. I might not be able to do this mentally. That's still smaller than 462, but the next time I increase, right, I'm going to get a number that's very close to 462, and I think it is, in fact, exactly 21 off. So I think my estimation is such that, let's see if this is correct, 1071 times 3 minus, no, it's plus negative. It's 462, 462 times, that's pretty close. The difference between multiples of these values precisely describes what the GCD is. Because all of these things can be divided by 21, essentially, and we can retain integers. Okay, how are we going to use this? This is going to be a little non-obvious, so I'm going to go in loops a few times. Essentially, you have to be holding 3 or 4 very precise pieces of information in your mind at the same time for this to all make sense. I haven't come up with a way to do this reproducibly, but every individual who's asked questions I've been able to get it to, so I'm going to essentially deliver a linear combination of communication technologies that worked on different students, right? Okay. Remember this thing. We're taking linear combinations of numbers to get a GCD, okay? I will tell you right now, it is going to matter at some point that that GCD can be 1. If A and B are co-prime, the GCD is 1. And that's telling us a way to multiply things together and get to 1, okay? So think about that one, okay. M to the E to the D equals M mod N. We are finding D, the multiplicative modular inverse. Now, that D is something that when we multiply E times D, we get 1. And so, if we have a linear combinations of things, where we multiply something together and add it to something else, we take 2 products, take 2 multiplications, multiply things together, add them together, and get 1. Over there, in extended GCD world. And then over here, in modular exponentiation world, we want to have some value that when multiplied by some other value gives 1. We're not that far off, because on one side we have 2 products added together equals 1, and on the other side we have 1 product is equal to 1. Now, on the other side over here we do have a modulo. We do not have the modulo with respect to the extended GCD. We haven't talked about modulo on that side of the things, right? So, we're going to use this modulo, and that's what's going to help us. Blah, 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 mod of the totient. It doesn't matter what mod is right now. It does matter one assumption we made of the totient, which is we required Carmichael's totient function to be co-prime with our encryptor. And how did we do this? We selected a prime encryptor, and we banned Carmichael's totient function from being a multiple of that prime encryptor. Fairly easy when we have prime numbers. And because we can use the same encryptor for everyone, helpfully, we have this additional benefit where we can sort of bake in that encryptor. We don't have to calculate that prime number. We don't have to check to see if E is prime every time, right? So that's really nice. So E and lambda, then, the totient functions are co-prime by construction. What does that mean? That means that their GCD is 1, which means that if I use the extended Euclidean algorithm over those 2 values, I will get a linear combination of values that is equal to 1. So I'm going to have 2 products that equal 1, and it's going to be a linear combination of these 2 values. And what is a linear combination? Product, right? We're doing multiplications, and what is the thing we need? We need a multiplicative inverse. And a multiplicative inverse occurs when we multiply 2 things together, and we get 1. Okay. So, here's the way that I express that linear combination. We have the encryptor times our calculated x value plus lambda then, Carmichael's totient function times our y value equals 1. But this is not just the multiplicative inverse. This is the multiplicative inverse modulo what value? This value, Carmichael's totient function. It's the exact same value. What this means is that I am dividing by this value. I am dividing by this value. And I am taking the remainder. When I divide by this portion of the expression, these 4 values in linear combination, when I divide by lambda then, it no longer matters what y is. Is it equivalent to 1 modulo this value? Do I have that on the next slide? I hope so. E, the encryptor, times x is equivalent to 1, the GCD. Did I say equivalent or congruent? What did I say? Pretty sure I said congruent. But they're equivalent. Okay, I said equivalent. I'm wrong. I can admit when I'm wrong. It doesn't even pain me to admit when I'm wrong. That's why I do it so readily. Okay, so the encryptor times the calculated x value. Wonder what that x value is. It's one of Bezos's identities. Right, there's the Seattle identity and the Florida identity. I was doing pretty well, and I'm like really losing my voice. What time is it? Oh, that is a long time to not have a voice. I don't have a backup plan. Okay. Gave the students a midterm in Salem today, so I don't have to talk for those 90 minutes. They loved it. Everyone was like, oh, thank you so much for this midterm. Oh, wait, did I tell you this joke? Okay. This is awful, right? You saw it in chat, right? Based term, right? So, like, I didn't want to give a midterm because I don't do anything that's mid, right? So I joked that, like, the tattoo I want to get is a tattoo that says keep Salem mid, right? Like, and so I was like, oh, but, like, I don't really do mid, right? I'm based, right? Because, like, we're not cool anymore. So, like, what is one thing that you can't argue isn't based? A number that's in base 64, right? Is necessarily based on 64, right? It's perfect. It's the based term. It can't be a midterm. It's a based term. Everyone hated this. Okay. I haven't told the other faculty yet. I'm not sure. Some of them have never heard the term based, which I'm very jealous of, right? Like, give me some of whatever they're having. Okay. Oh, I should check chat. Okay. We do have viewers. Why not? Well, 3 views, but definitely the person that's not here is watching the whole time, right? That's very high attendance, because that's when we were at dinner. Shout out. Can I get a shout out to our viewers? Shout out to Haley. That is very impressive, right? Like, because you can't fake closing it for like a couple minutes unless you're actually there, right? And it's not like I usually check to see if we have concurrent viewership, right? So, good job, Haley. Well done. If you see this at home, like, comment, subscribe, or whatever the like not irony-filled way to say that is. Irony is poison. Oh yeah. Okay. What are we doing? The extended GCD algorithm, right? When I looked this up on Stack Overflow, I had to call it the extended Euclidean algorithm pretty much 100% of the time. Doesn't seem like anyone's calling it extended GCD. I think the real reason for that is a lot of languages have something built in called GCD, and you're trying to avoid a namespace collision, right? Okay. I can use, I'm going to say this again, I'm going to say the exact same thing. I can use the extended Euclidean algorithm to find a linear combination of the 2 input values that is equal, not congruent, equal to the GCD. If my 2 input values are coprime, by definition the GCD is 1, which means I have a linear combination of input values that is equal to 1. If I take that linear combination of values modulo one of the 2 values, then I have a linear combination of values that is congruent to 1 with respect to that mod. And with respect to that mod, I can remove one of the 2 products because that product is congruent to 0 with respect to the mod because it is the multiple of the mod. 5 is congruent to 0 mod 5, n is congruent to 0 mod n, lambda of n is congruent to 0 mod lambda of n, which means for all b times lambda of n is congruent to 0 mod n, mod lambda of n. So I have a product plus 0 equals, a product plus 0 is congruent to 1 mod the other value, okay? Which is exactly what it says there. Which means I have 2 values that when multiplied together they get 1, which means that is a multiplicative modular inverse, which means I can calculate multiplicative modular inverses with the extended Euclidean algorithm only in one very specific special case, which is the special case of the values being coprime. Fortunately, I was able to reach out to Rivest Shamir, S-H-A-M-A-R, and Adelman, A-D-L-E-M-A-N, shortly before class, And they went back in time and they required those two values to be coprime, just so this lecture made sense, because otherwise this lecture is going to be a bit of a disaster. And that's the solution. Okay, this is bad. How do we fix it? We're going to implement the extended Euclidean algorithm. All those quotients we were throwing away, right? Let's bring them back. Quotients back. All right. Okay. I can't name a single Backstreet Boy. Ground thrust. Oh, that's supposed to say truth. Thrust and truth are unrelated. So I've noticed, I haven't mentioned this to you, the typos I make are things that sound the same to me. They're not things that are next to each other on the keyboard. So I have a audio file to QWERTY translator in my brain, which is not the correct way to type. Okay, so the extended GCD. Let's do it. I do regard this as self-documenting, and I'm sure there's not any questions about it. So I'm just going to imagine what questions you would have if you did have questions and try to respond to those. So don't let me bore you too much. If you're looking for something to do, many of you have computers here, just pop those little laptopies open and start clickety-clacking away, right? Okay? You can write this in any language you want as long as it's C89. What's going on here? I did not realize this the first time I implemented this algorithm. I could not figure out why they were using the term old. This is an iterative port of a recursive algorithm. Old refers to what those values were in an earlier calling function, or an older calling function, whatever you want to say. When Euclid was describing this algorithm, perhaps there was just something called R and just something called S. And you're thinking, why are they called R and S? You're working with a quotient, and you need to keep track of more than one quotient. What are the alphabetical letters after Q? Q, R, S. That's where the name comes from, right? So Q, R, and S are all referring to quotients of varying sorts, okay? So we're going to initially populate, essentially, this, I don't know. We can think of it essentially the way it's working inside the physical computing devices. These values are pushed onto the stack, the same way arguments to functions are being tracked. Intuitively to the physical computing device, it makes no difference whether this is implemented as a function, which does some operations and then gets an instruction to go to a certain memory address, and that memory address is back at the start of the function again. Or if we implement this as a while loop, where there's a series of instructions followed by a memory address that points to physically identical. I suspect GCC implements them differently. I suspect Python implements them differently. This is actually just the languages being wrong. We should write better compilers that create the exact same code, right? And I said we should write better compilers, and University of Illinois Urbana-Champaign started the LLVM project, the most successful compiler project of all time, 10 years ago, and for all I know, that is going to be the same at some point in the future. But GCC was unable to solve this problem. It is possible LLVM will. And if we go to the Rust talk, we'll probably hear about LLVM, because it's an LLVM language, which stands for, what does LLVM stand for?
Low-level virtual machine.
Low-level virtual machine? Is that what you said?
I think so.
Okay, that makes sense. So it is pretending to be a computer that was designed by people that design computers instead of Intel, which is a company that designs things that don't melt, right? Completely different design criteria.
It's an orphan. It doesn't stand for anything anymore. That's what it stood for initially.
I think it stands for Lawrence Livermore Vaginal Laboratory. Yeah. Whatever. Okay, we're doing our best. Okay, so old R and old S are legacies of this being a recursive algorithm, and we had to have some way to refer to them. How did I refer to them in the C programming language? Well, I actually created an array of size 2 named R. And I just had 0 and 1. I just swapped them. So everyone hated that. Okay. Well, R is non-zero. We remember that. That was our exact terminating state from the EA algorithm. Remember when we were doing electronic arts earlier? We looped until something was 0. Now, the thing that was 0 in that case, we called it B. And what was B? We were doing sort of repeated subtractions over time and b was the current remainder. So that r, which is 2 letters after q for quotient, is some notion of a remainder. This is perhaps should be a little bit unsurprising to us when we look particularly at this exact line here. What is that line? That line is computing a remainder as follows. We don't care what quotient is at this time. We're going to multiply quotient times r. Okay? So we have quotient times r, and we subtract that value from old r. This is a product being subtracted from old r. What is old r? Old r is the thing that was divided by. So this is the, oh no, it's the one on top, which is the north. It's the numerator. We've got our north here. And then what is our Dakota? That's our Dakota, right? My partner has a coworker named Dakota, different spelling, physicist. Let's hear it for physics.
Different spelling.
Different spelling. Wait, that's a privacy violation. Never mind. It's a different spelling. It has 17 silent letters in it.
Oh.
Yeah. And 24 pronounceable letters. The silent letters are all non-printed characters. Okay. Okay. This is a remainder. This is the exact inequality we wanted to be equal to 0 when we were causing the Euclidean division problem. That's the thing we divided by, subtracted from the quotient times the denominator. The denominator? The Dakota. It's the quotient times the Dakota, okay? Right? So we subtract from the north, we subtract the quotient times the Dakota, right? So that gives us the remainder. So these r's are always going to be holding some notion of remainders, which is extremely non-confusing because we don't know if r represents the letter that comes after q for quotient, and so that's holding a type of quotient, or a remainder. So, far be it from me to comment on software engineering. Never, under any circumstances, name your variables like this. It is ambiguous to me, completely understanding this algorithm, and thousands of people having seen this being the de facto reference solution, right? It is unclear if that is intended to be a quotient or a remainder. I don't know, right? At least there's one thing called a quotient, right? But I don't know if I'm confused or someone else is, right? Okay, so anyways, here's our remainder. We're calculating the remainders, but we're calculating the remainders with respect to 2 distinct values, right? We have r and s, and so what is going on here? Initially, r is holding the values over which we are computing the GCD, right? And what is s holding initially? Well, we have a 0 and we have a 1. Well, s is the coefficients of the linear combination. I don't know how else to say this. 1 times a plus 0 times b equals a, the current candidate value to be the remainder, because the ultimate GCD is going to be the first argument. Why is it going to be the first argument? We put the maximum first and we put the minimum second. So S will be dynamically updated to contain the coefficients of the linear combination that describes the GCD. So these values, S and old S, we can use to determine what the multiplicative modular inverse is, but most importantly, this is Bezot's identity, right? Bezot's coefficients, and you don't have to believe me, it says so right here. Old S. It would take quite a bit of paperwork to determine that old S is in fact the one that contains the identity, but we could do it if we had to. We'd just print out the values and run this a few times. So the coefficient is old S. So these are the coefficients of the linear combination. These are the current working values. These are the initial calling values. And then at the end, not R, but old R, right? The previous R, because the current R becomes 0. So the non-zero of the two R's is going to be the GCD. That didn't make any sense at all, did it? Yeah, not to worry. We're going to write it in Python, a language. It is so simple, even undergraduates can understand it, right? Not my undergraduates, of course. Undergraduates taught by someone that understands Python. Okay, what's going on here? We don't care. Take it out. Okay, we're only going to look at old s. Why am I only going to look at old s? Okay, so say I've got a linear combination of things. I have an equation of the form ax plus by equals c. And I know a, x, b, and c. I can compute y. There's one unknown, there's one equation. It is a linear combination. You can solve it using this little thing called division, which is now allowed again, right? Because we had to invent division first, but we have it now, and we can use it to solve linear combinations, right? So we actually only need one thing. So don't worry, we deleted all of that text at the bottom. And that was the confusing text, right? Because we all found this trivial. No? That's what I thought too, right? So there maybe there's a little bit of confusion going on here. We're going to advance the slides a little bit, but before I do that, a variable is going to show up that's called t. T is the letter that comes after R and S. When I deleted all of this nonsense at the bottom, we were using this mechanism right here to calculate the second value in the linear combination. T is the other value in the linear combination. I'm going to reintroduce it. So I'm going to have R, which is the current candidate for GCD. Then I'm going to have S, which is the coefficient of A, and T, which is the coefficient of B. Why am I reintroducing these values? Because the notational convenience is quite high when we switch to a recursive solution, which I found easier to understand. If you are confused by the reemergence of T, it is simple to imagine there is an additional line here that just says T. I think the T values are all initialized to 0. I've been wrong before, right? And you don't need these lines here. You can just check the reference code on our favorite pedia that starts with wiki, right? It's Wikipedia. We're all Star Wars fans, right? May the 4th be with you. I don't know what month May is. It's the 5th one, right? So May 4th is 5-4. And what is the prime factorization of 54? 3332, right? It's 27 times 2. 3 cubed times 2. Yeah, I know. Okay. Yeah. Lock in. Okay. All right. This implementation does not calculate modulo, so I'm gonna make a notational convenience here. I'm going to do my best to keep with the pseudocode stylistic guidelines here. They didn't write percent, or they didn't write slash for div, so I'm going to write mod. So rather than saying old R minus quotient cross R, which kind of weird they write cross instead of times here when they write div here, but like I didn't invent pseudocode, right? I did invent a pseudocode compiler. It's called Python 3. It's available in the App Store on Windows. It's called, no, yeah it is. It's called Python 3 on non-Windows systems and Python on Windows systems, right? Does that sound right? I've been prepping a Windows development talk for next week. Remember, I like doing things because they're harder for no reason.
Have you thought about doing these sort of Python examples in your slides instead in a language that has type flags, the Swift programming language?
The Swift programming language? No, I mean, I thought about doing it in Go. Are you a Go appreciator?
No.
Okay. I had you down as maybe like in C#. Did I make that up?
I've never programmed with C#.
Okay. Does anyone here do TypeScript? Okay. Yeah. To me, the competing language is TypeScript, and the reason I'm not using it is because of the integer problem.
They've just rewritten TypeScript to Go.
I saw that. That is very, very cool, right? Which means VS Code is written in Go, right? Everyone's favorite IDE. Does anyone like an IDE better than VS Code? Don't even answer that. I'm just going to assume you like VS Code, right? That's mandatory liking VS Code. My favorite IDE is, of course, Notepad++, but that's neither here nor there. Okay, I've got this code. I'm gonna turn this recursive, but in order to turn this recursive, I have to throw T back in. They call that spilling the tea. So I couldn't even say that was. S and T are coefficients. They are things we multiply times A and B. In that line that says output, I say R, T, and then I say some operations on S, right? And in line 5, I say R, comma, S, comma, T. I'm changing the position of the T and the S. Why is that? Because in line 5, I'm also changing the position of the A and the B. If T is what we multiply B by, B is in the first position of extended GCD, the recursive call in 5, which means that the value returned for the coefficient needs to be in a different position because B is in the second position rather than the first position. Should I call it the one? Well, we'll say B is on the left-hand side of the recursion, which means the left-hand side coefficient is S, and the outermost function, B, is on the right-hand side of the arguments, which means the right-hand side coefficient contains S, which is why S is in the second position in line 7, and it is why T is in the central position in line 7, and it is in the terminal position in line 5. So we are moving S and T back and forth and performing modular operations over them, the same way we are moving A and B back and forth and performing modular operations over them. We're performing the same operations on essentially R, S, and T. And these R, S, and T are computing linear combinations over A and B. And they're also computing the GCD. In this case, when I'm computing the multiplicative modular inverse, at the end of the equation, I drop the GCD on the ground, never to be seen again. I drop the second coefficient on the ground, never to be seen again, and I only look at whatever the return value in position T is, right? That sort of middle return value. But you can implement this however you like. In my C code, I have a return value, I return the GCD code, and I provide a pointer to an integer, or a 496T, and I load that 496T with the relevant Bezos identity, which in this case is always Seattle, because VS Code is written by Microsoft in TypeScript that transpiles into Go, a language developed by Google, which means West Coast, Best Coast.
Well, it doesn't transpile into Go, it still transpiles into JavaScript, but if the transpile is written into Go.
Oh, that's much less cool than I thought it was. Really?
Previously, it had been written in TypeScript.
Wait, it transpiled itself? It was self-transpiling?
It was like PyPy.
I'm somehow in two ways both unhappier than I was several minutes ago. I saw TypeScript is written in Go now, and I was like, yeah! And I didn't assume that meant that they were transpiling it into JavaScript, another bad language using Go. And the reason I think that, and the reason this is relevant, is that I know what language Go is written in, and that language has integers in it. And I was assuming this meant that I was going to get integers in TypeScript at some point, but obviously that was a little bit too optimistic.
Is Go not self-hosted?
It probably is. It's fast.
Also a great mascot.
Oh, what's their mascot? Did I miss it?
The little icon thing there.
The Gopher.
Oh, the Go?
That's what it's called? That's great.
Is it on? Let me just see. I'm sure it's self-compiling. Yeah, it's mostly written in Go. Go in assembly. Look how gosh darn adorable they are.
Oh my gosh, is that an infinite length tape? So that would be a real Turing machine?
No, see? Like it's finite.
Oh, sad.
Unless it's infinite on this side. Perhaps it has a bijection to the naturals, but not to the nths. Get me out of here. Okay. Oh, with the fixed point combinator. You see, that's an infinite tape. Right? That's infinite recursion. How much input lag do we have? Look at that. Okay.
We have 2 viewers. Oh, one of them's probably. Yeah.
Oh, I wonder if I count. Yeah.
You do,
I count in base 64. Okay. So here's everyone's third favorite programming language after Go, TypeScript, and the Lambda calculus, Python. Yeah, I wrote the extended GCD. And I didn't have to do this, I want to point out. I could have written a list comprehension in line 4 and not used any variable names. And I didn't do that for you because I care about you and I didn't deliberately want to confuse you, right? But I am, in fact, strange enough that I considered doing that. But anyways, we compute the extended GCD, and it's going to return, in the base case values, A, 1, and 0. What is that? Well, 1 is the value we are multiplying by A to get A, right? We return from that, and we calculate our S and T, so perhaps that is A, 1, and 0, perhaps it is some other values. We leave the A as is because the GCD is not changed no matter how far we go back up the call stack. The T is unaltered because that is the coefficient of a percent B. Is that true? Maybe it's B, right? One of the coefficients is unaltered, and the other coefficient is computed as how much by which we must multiply one of the coefficients, or one of the intermediate values in order to get to the change to the coefficient. Does that look confusing? Of course it does. But you know what it's doing. You know what it's doing from the 147 example and from the 462 example. We're computing by what we must multiply these larger A and B initial values over time, and we're doing that by multiplying them times each other. When we take the product over all of the quotients, these are all perfect divisions because there's no remainders left. So we just multiply them all together, and that at the end, that is one of the two factors of the linear combination of values. Running out of words here, but essentially we're figuring out by which we multiply values to get to 1. That's all we're doing. This is confusing to you, write it and print every line. Okay. Here's an example. There's the extended GCD. Not too bad. Let's get this to run. Wait, what's it called? GCD? 1071, 462, right? Did I make that up? Okay. And that is 1071 times -3 plus 7 times 462. And those are the 3 and 7 are the values we computed. I computed manually in front of all of you, right? But I had the signs backwards, which is why I got -21 when I checked it, right? But it's easy enough to invert the signs. Let's instrument this code, perhaps. Wow, I just voluntarily had the thought, I wish I was in Jupyter Notebooks right now. Did you feel that? Oh my goodness. I have never felt that feeling before. That was quite strange. Okay. All right. Okay. We have our extended GCD. I think this base case is relatively uninteresting. But let's look at this one, okay? We're going to print what R is equal to. Does anyone remember how to use Python format printing? Does this look like Python? Yes? No? Anyone help? No? Well, yes? We're going to print something. That's not true. I don't know that this will definitely print something. This is how objects were invented, by the way, right? I have an object that contains 3 integers. Okay. And then what was this thing? We're going to do whatever this is. That's probably legal code in Python. I don't know. Ah! Where's the unexpected indent? Name S is not defined?
You're not in the function.
Well, yeah, but it should know that I want to be there. Lambda of R, S, T, A, B. Okay, that worked. Standard GCD. Is this how you do your software engineering?
I don't even know why I'm doing this, but here we are now, right? So like,
Don't you wish you were Google Colab?
what? No, they're all, wait. No, they're all spaces, right? Oh no, they're only spaces because it's in the terminal, right? The terminal is reading my tab character, but it's directing a tab character to Python. The Python interpreter is displaying it for spaces. Well, there's only one way to do it. It's time for some monkey type. Is that not allowed in Python? What did I do wrong? Oh, is that not?
Yeah, I think you might have to do not written out.
Yeah.
Not to worry, I have a plan. What's everyone's favorite text editor? Notepad++.
Android Studio.
You were close, Ari. That's my second favorite. This is how Jupyter Notebooks were invented. I'm committed to the bit at this point. I can stop anytime I want. Okay. C, tab. Okay. No graceful mod here. Hold on. Why am I not using Vim?
Felt like it was still used for
This is what I'm like in real
You're
life.
not in WSL.
So on my desktop, I have Vim on Windows,
Yes.
and I don't actually know how to maintain your Windows packages across two different Windows devices. Okay, and I don't feel bad about not knowing that. What was I doing? I shouldn't have opened WSL. I should have turned on Podman and entered a container that had Vim.
Wouldn't you have had to turn on WSL to open Podman?
Yes, it's exactly as slow. But when it's in Podman, it feels like you have no control over it, so it's fine. Vim, what are we doing? egcd.py. Is that what I want to do? You're not supposed to import star. I've heard that's poor form. But the coding style guide that does it specifically says, it doesn't say if you're in class, but it says if you're in the interpreter, you're allowed to do it. And I was like, hell yeah. I only use Python in the interpreter. Never written a Python script in my life. Okay, extended GCD. 1071, 462. Oh, wow, it worked. Okay, it worked. You can see the one going back and forth, right? This one became that one. This 3 became that -3. This 7 becomes that 7. Right, so this is computing the ultimate coefficient. These are transient coefficients. So they're coefficients at the lowest level, right? The R value remains constant all the way through because it's the GCD. And the way this works recursively is each recursive step has the same GCD because they're all multiples of 21. Right? Ta-da! Relatively simple to write. Do I have anything else? Oh, what's this? Oh, I installed command line R the other day. I made a graph. There's some good stuff in here. I was learning observable. Look at that. Anyone love JavaScript?
I love D3.
Do you is observable good?
I don't know.
Okay.
Well, I've used D3 in my undergrad data visualization class.
Okay.
It was much more annoying than using ggplot.
It is more annoying? Okay.
So much more annoying.
Okay. Because someone was like, hey, do you want to teach data visualization? I was like, can I do Streamlit and observable? And they're like, Heather's going to teach data visualization. I was like, that makes sense, right? There's like, I know what pixels are. And they're like, go home. I'm like, okay. Here's an example. I already did that. Wait a minute. Who dealt with negative values when they implemented 496T? Not me. That was a problem for future Calvin. And little did I know, a month later it would still be a problem for future Calvin, right? So future Calvin is looking with some anxiety at their extended GCD code going, why did future Calvin be the one responsible for dealing with signs in this? Anyways, I have 64-bit extended Euclidean algorithm working over unsigned values. And it took forever. But I think it was still faster. So, anyways, this is the technique. You can track either orders of magnitude or you can track signed bits. Why do we say a signed bit? It only contains 1 bit of information. Of course, I just used a 64-bit integer to store the signed bit, right? Because those 64 bits, the company's paying for those, right? I asked for a machine that had a 1-bit type, right? My boss didn't give it to me, right? So I shouldn't have to pay for that. Yeah, that's how it is. It's pretty easy. It's pretty straightforward. Any questions? You could all write this. Are you going to implement it iteratively or recursively? Well, given that stunning participation in the question and answer section, I was going to start live coding the undergraduate midterm and let you watch. Does that sound more fun than whatever else we'd be doing? Yeah, cool. All right. So, I apologize for not forcing you to do the midterm, right? Because do you all know there's these entities that are referred to, I don't think they exist in real life, to be clear. I've seen them in situation comedies, and they're referred to as teenagers or adolescents, and they have to be forced by their parents to have fun, right? That's what I am. I have to be forced by my parents to have fun. And my parent function is myself because I'm self-hosted via Hyper-V, right? So I'm going to force myself to have fun with base 64, and I want to apologize for not forcing you to have fun. I'm allowing you to watch me have fun instead. But I suspect as we go through this process, you'll become quite jealous and decide to voluntarily participate in the midterm as well.
On the previous version that you're showing with the old R and the old S, why didn't you make a joke about being like saying something like we're all R and earlier?
I didn't think of it. I have a confession. The thing that it actually sounded like to me was World War, which is the World of Warcraft raid from 2010. This thing. Anyways, so I was trying to not make a gamer joke. I actually do have an answer to that question. There's this Machinima song, Meet Me at World War by Nim and Summergal. Which we probably don't need to. Oh, I can't watch that on stream. I'll get instant banned. Okay.
You're gonna have to stream to mega.co.nz.
That's, or in Discord. You can just stream in Discord. Okay. So this is what you all would have seen. All of the students clicked that link. Not really a fan of doing things that way. So I'm going to instead click this link and then quickly grab this thing, which is identical except it says .git at the end, right? But pressing that little button gives me the serotonin hit from like that. I mean, look at it. I love pressing buttons. Okay. Someone broke into my computer and opened Windows subsystem for Linux on it, so I might need tabs. I don't know. We'll see. Okay.
No,
broke out of. I don't know what I was trying to say.
Did you mean for the last one to be a slash?
No. Why would you do? I'm fighting for my life up here. All right. Okay. Is it checkout?
Clone.
Oh, it's clone. Oh no. Oh no. Oh no. How would this usually? Wait, I'm not.
It's because it's a private repository.
Yeah, but I put in my. I thought I set up authentication earlier today.
Did you set the key? You have to do the SSH.
Yeah, I thought I did it correctly. That's why I'm confused. I'm wondering what I did wrong, basically. I don't really want to show a GitHub private key on stream.
You
right?
don't have to show a GitHub private key on stream. If you actually set it up, you will find out if you set it up properly when you check out the actual SSH link instead of the HTTP one.
Oh, is that what it? Oh, okay.
Yeah, that's what you have to do.
We'll see this. Well, apparently not.
Even GitHub knows you didn't do it.
GitHub's calling me out here. Ooh, I can use the GitHub CLI.
GitHub CLI.
So, I mean, we'll see. I have an ingenious plan. I'm going to download the zip.
Version control.
The real problem is I'm essentially unwilling to use a laptop except when I have to teach this class, so nothing's configured on my laptop. But I'm supposed to have a new one ordered.
You're just not thinking institutionally enough. What you got to do is just have your desktop at home always on and RDP into it.
So yeah, Professor Rumble unironically does this. I thought he was kidding the first time I said it. I was like, ha ha ha. And he was like, yeah, it's great. I was like, but he has a rack server now. Right, I don't spend money on hardware. Okay, so what's going on here? Well, WCell's already booted, and through the mount interface, it can reference locations on the Windows file system. So I was just going to take these files and copy them to home, and then over here in my other Windows subsystem for Linux terminal, they're just going to show up. And yeah, I successfully used Git, right? So I think we can all agree that was pretty impressive. At this point in time, I realize I actually have no idea how to open base85.html from inside WSL. If I just type Firefox, does it work? I've opened Firefox from in here before. VS Code is my favorite Go language program. It's written in Go now, I hear. I'm tired of waiting for that. Even when I'm pretending to ironically hate WSL, it's still too slow for me. Okay, so here we open base 85. F1. Okay. All right, implement base85.py behavior. Okay, so you all know base 64, right? Base 64 encodes things. What do I have in here? So we can base 64 encode base 85.py, and we just get like the base 64 junk output, right? Probably not too bad. Base 85, like, isn't really a thing. Base 58 is the one that Satoshi Nakamoto uses for Bitcoin. And why is that? 58 is 6 fewer than 64. What did they take out? All of the L's, 1's, 0's, and O's, because they look the same. Sure. So anyways, base 58 is around and the crypto people use it. I thought it was funny that the two most likely bases I would use after 64 were 85 and 58. So I also think that that was like a free added benefit. 85 is used by Git. It's used in Git diffs, and it's also used inside PostScript and PDF, apparently. That's what Wikipedia says. I didn't like go rummaging through Git to see if they have an internal base 85 implementation. It's also called ASCII 85, and I couldn't get this to work in containers, and I think the reason I couldn't get it to work in containers is it seems to only work on, I can't talk and type. Why did I not do -y? This seems to have some unmaintained Ruby dependency that breaks on some devices and not others, so I don't know if it's going to work on my device right now. But it looks like I'm installing Ruby, and that makes me think this isn't going to work. Okay, it works. Cool. Hold on. That's extremely unusual behavior. What is happening here? Why is there a new line there? I've never seen that before. Right, it's not quite... Oh, it was exactly at a text wrapping boundary, I think.
It's actually just base 86, and the 86th character is the new lines.
I mean, it does kind of look like that. So I think these lines are 80 characters long. I don't know what's going on here. Maybe they don't want to line break this one? Well, now, what does my reference implementation do? See, I put it on the same line. I didn't know that. Okay, so this, I found a deviation between my reference implementation and the actual reference implementation. And I don't really know what to think about that. I need to try this on my other ASCII 85 I have at home. Anyways, if you are sitting at a Linux terminal and have a Linux device and you want to probe some of the behavior of ASCII 85, that is an academically interesting thing to do. Anyways, I'm going to try and implement this. And I'm going to do this in base85.c. I get to name this one base85.c because base85 isn't taken. That's pretty nice. I'm not sure what all I'm going to need, but I'm pretty sure I'm going to need standard I/O. Oh, my hands are going to hurt. I might have to sit down. Okay. Wow. This feels weird.
Raise them over the desk.
I think I want to be dramatic. Okay. Include standard int.h. I don't know if I'm going to need standard ints, but there is one aspect of the C89 language I don't like, and it's the ability to just say how many bits I want my integer to be. So this is a C99 library. Sue me. Actually, don't do that. Don't sue me. Sue Linus Torvalds. Okay. What am I going to do in here? Well, am I going to implement this entire thing inside the main? Probably not. I'm going to look at command line arguments because I provided the command line argument of the file name. So I have argc and argv. What's argv stand for? Does it really? Do we know? I told you it stood for argument vector. I don't know if that's true. It's actually a linear combination of arguments for which every coefficient is 1.
IBM says it's argument vector.
That makes me less confident. Thank you. Okay. So what's the first thing we're going to do? We're not going to check to see how many arguments there are. We're going to stare directly into the sun. We're going to fopen. What are we going to fopen? We're going to fopen arg1. Okay. I think the return value of fopen is a file star, but I saw some code by someone I trust. I don't remember who I trust, but it could have even been like a kernel hacker or something. Apparently these things are also size keys. Because they're the same as every other pointer. They're just a location in memory. And the biggest location in memory is the size of memory. So anything that's big enough to hold the size of memory can hold any location in memory. So you can just put a size t there. I like that better. Why? I didn't like the capitalization. It stressed me out that file was all capital. It always felt like I was in the wrong language. So when I just glanced at my code, I always thought it was wrong. So I think my personal style guide is probably going to switch over to size t now. And I have source amnesia on where it's from, right? Okay, so we're going to size t fopen. I'm not going to compile this under C89, but I'm going to try and stick to the C89 guidelines. So I'm going to try and not... what am I going to try not to do? I'm going to try not to mix variable declarations with live code. And so I'm going to need some working values. I'm going to need, I guess we'll call it var. I'm going to avoid having some magic numbers by defining the offset as 33. And what is that? The first 32 characters of ASCII are like special characters or control characters or something. We shouldn't think of them as the first 32. We should think of them as the first OX20. So when we are converting binary data to printable characters, we look at a subset of the ASCII characters, and we start our subset at the longest running train of printable characters. And the longest running train of printable characters begins right around 33. It might begin at 31 or something, right? So I'm going to add 33 to these, what are essentially base 85 numerals. And the base 85 digits are going to be the ASCII characters numbered 33 through whatever 33 plus 85 is. And there's off by one errors all over the place in my speaking right now. It doesn't matter, it's quite simple. So I'm going to use an offset. And that offset is going to be a uint32t. Is that how you do defines? Does that define look correct? I think that's correct, right? I'm going to have a variable. Okay, this looks good.
Do you need an opening mode
Wait, an opening? What?
for the file open?
Yes, I have to say. Is that what I'm thinking? I didn't mean to do capital. Yeah. See, like to me, there's the strong usefulness in not having any capital letters in your code, right? Except the constants. I don't know. It works well for me. Who loves do while?
Are we being good programmers and doing checks or not?
No, not on mid. It's timed. Yeah. So I'm also not going to compile with all the flags.
Cool.
It's not cool. It's wrong. Okay. I am going to freed into var. I'm going to freed 32 bits at a time. I'm going to do size of uint32t, which has to be 4. I can hard code that. That's 4. I'm going to do one of them. See, they call it a file star. That's okay. And I'm going to read them from when I read that var in, I'm going to perform some operations on that var, and I'm going to, at this time, reveal my elaborate ruse. This entire midterm was about endianness. Remember endianness? Remember our good old friend endianness? Ari doesn't. Ari accidentally avoided endianness, thereby avoiding the learning objectives of this course. The thing to learn about this course is that the computers are deceitful. They are trying to trick you. They are trying to bamboozle you at all times. And the way they bamboozle you is they put the bits in completely arbitrary orders that you would never guess. And then when you ask them politely to tell you what order the bits are in, they tell you the order that you already thought, even though you know they're lying, right? Because the computers, they're under no obligation to tell us where they're keeping their electrons, right? But I have a good friend. My friend is called the internet. It's a bigger, badder, and scarier computer, and it can bully my computer into putting bits into certain orders. Now, of course, this order is the wrong order, right? But it's at least a predictable order. So I'm going to go ahead, and I'm going to grab ARPA init, and I'm going to HTONL. Do I even want to do that? It's easier to do this manually, isn't it? No, I don't know. ARPA init. I'm not even going to check to see if I was already in the correct endianness. I'm just going to HTONL and hope it works. We're feeding into var. We're going to HTONL var. And what does this do? This reads 32 bits off of the device, and then it scrambles the individual bytes around to be in a more friendly order. Why are we using network order for something we're doing locally on our device? The exact same reason we did with SHA-256, the usefulness of base 85 and 64 and 58 and 37, 32, hex, and so on. All of this is to enable us to transmit information over wires. Hex is quite useful because it's basically always in the same order. All of the other encodings are going across byte boundaries, so they have to take into account endianness. I thought about giving an assignment to do octal, for example, which also goes across. It's 3-bit chunks. That was a little bit too mean, so I didn't do that. So we've HTONL'd our var, and then it's a simple enough matter to write a cute little loop. And I'm going to use a variable I for my loop for I equals 0. Put a pin here, cognitive pin. Everyone remember where we are? Okay, take a snapshot. Okay. I is less than 5. When I did this midterm myself, I forgot the order you put things in a for loop, and that was 80% of my dev time. I got endianness correct on the first try. But I put the incrementer in the middle of my for loop instead of at the end of my for loop, because you increment while you're in the for loop, right? So it made perfect sense to me. Does that look like a C language for loop to all of us? That's good. Surely we know what we're doing. What are the odds we don't? Okay. What am I going to do here? Well, I'm probably going to... Have you all seen putchar? This is printf for a single character. It's just a nicety. I didn't learn about this for years. It showed up in a Stack Overflow comment, and I've worked it into my workflow. I predominantly use putchar to just throw new lines around when they come up, right? It's a little bit nicer than writing out all of printf. It's actually more characters. I think it's just, to me, conceptually easier to think about single characters, right? I have so much cognitive overhead thinking about null-terminated strings in C that I'm always nervous about working with strings unless I absolutely have to. This code I'm going to write right now, it's only going to use characters, and I'm not going to print anything at all. So I'm going to put char, and also perhaps this one is a little more common, put C, right? But put char is the hard-coded one to do directly to output. And I'm going to put char var 85. I'm going to take the 85 lowest order amounts of information. This does not evenly divide bits. There's not any way to evenly divide 32 by 5. I thought there was. I checked very carefully. I wrote myself a little proof called counting necklaces and found out it was actually indivisible. Remember counting necklaces? We had 2 left over, right? And those were the necklaces that contained all agates and all beryls, right? So unfortunately, there was no way to evenly divide by 5. So I'm not even going to pretend that. I'm just going to do mathematics, and I'm not going to think about binary at all. And I can do that. So on the course of ALS, if it says Calvin only talks about binary, that's false, right? I'm doing information theory without respect to the underlying electrical engineering right now at this very moment. Okay, all right? Is everyone? No? No one's taking notes? Okay, well, that's fine. And as soon as I take those pieces of information, I no longer need them in my program. I've output them to that. Oh, is that Euclidean division? And perhaps at this time you see why I thought this was such an unbelievably cool midterm, right? It's based, it's Euclidean division. That's all you need, I mean, as far as I can. I don't know if this will actually work, but it'll be kind of close, right? And how wild do we do this? So I need some way to see if freed is working. And it appears the return value of freed is the number of items read or written. Okay, so I'm going to say what I want to do, right? So it's going to return non-zero if it reads something, right? So I should put the freed inside the case statement of a while loop, right? That's definitely what I should do. Okay. This was your idea.
Fun fact, if you're compiling in pedantic mode, it won't let you not use the result of the freed.
You can cast it to void.
You can't? Okay.
I don't know that I've for sure tried that with freed, but most of the things you're supposed to null check, you can void cast. You are not allowed to do that until you become a professor. Okay. I'm also not allowed to do it. What deviations have I made? What transgressions have I allowed myself? I'm not line breaking after 80 characters at this time. And I'm not doing the little caret, squiggle, squiggle. No, it was a less than, squiggle, squiggle, less than, and wrapping this thing, right? So I'm only doing the encoding right now. Is this going to work? Probably not. What is my terminal doing? Okay. You see how I got all the warnings to go away? Did you see that? Just that little W flag there? I guess I'm back to files next time I go in bin. Is that wrong? Seems pretty bad, right?
This feels wrong.
Doesn't this feel wrong?
There's a lot of empty space there.
I got a blank space, baby. Okay.
Did you do anything with the offset at any point?
That's a great question, Ari. You're looking at the code. What do you think?
I don't think you did. If you did, I wouldn't be able to see it because the offset is in like a very purple color up there, and it's really hard to see on the screen.
Is there an obvious way to
change the colors or to turn off syntax highlighting?
I'm not turning off syntax highlighting. We've done that before. It makes me feel like I'm writing text.
In your text editor?
It's code. Okay.
Oh, color schemes.
Oh, it's the Vim scheme, isn't it?
You have to save before anything changes. I think.
Oh, real?
Real and true.
So what I need is a Vim color pack.
I think if you go back to settings, they have a separate color schemes in the hamburger menu under appearance.
Oh, okay. Which one do we like? Ooh, this one looks good.
All of the purples. Oh, that should look slightly better.
No, it's just Vim colors. How do I invert the colors of my monitor? That's Discord. Is it raining? Is there a train going on top of the building?
It's under accessibility. to accessible. Yeah. Color filters.
Let's go with that.
And then go back up. Turn the switch that says off to on. And then select inverted at the bottom. Dark mode.
What was I doing? There's no way that's better, is it?
This is better.
That's better?
The
Okay.
issue is that the contrast between the purple and the black was really low.
Okay. Offset, right? I'm gonna put based instead of base.
Is casting to a U32T necessary in this case?
It's for documentation. I know I'm being sloppy about some things, not about others. It's just like, it doesn't do anything. Oh, it didn't compile?
No. Ah.
Oh, that's pretty good, right? And then what's the ref solution? And okay. In Biggin. So,
It looks almost right.
doesn't it? Do you see what's happening here?
Endianness.
Worse. It's anti-endianness or something, right?
Spartianness.
So we have to reorder the bytes to get the bits in this order, and now the bits are in the wrong order. So the bits and the bytes were in different orders with respect. So, not to worry, I have a plan. There's a very simple way to print out these letters in reverse order. We just have to change what we're dividing by, essentially. Right, so I'm going to add another value. Let's see. It's the Dakota, the denom. This North Dakota thing is going to save my life, just so you know. Yeah, that's incredible. And this thing is equal to last one, right? I should say based. Is that right? No. So I'm yoinking that because I want to reset it here. Okay. What do I want to do? Well, I want to Dakota by the denominator. And then I want to reduce the size of the denominator. So I'm taking the biggest chunk first. I don't know if this is going to work. We'll see. Does it look like it'll work? I don't see any obvious clownery and perhaps tomfoolery. Maybe some rakishness. I'm always surprised when my code works too. I forgot to compile. Wait, what am I doing? I can just do this. That seems ludicrously bad, right?
We've added lightness.
Oh, we were close. I guess I thought that would work. Does it seem like it should work? Oh.
I'm having to remember Vim commands, sorry. My Vim brain is starting. Okay, there we go, yeah. It's not percent. Oh, that's not bad at all. What's the reference solution? I'm putting in a new line.
That looks pretty much right.
Okay, so we just have to have line breaks. Oh, my students said this was hard. Look at, you could have done this in 10 minutes, right? It took me half an hour, right? But you would have been fresh, right? This was at what time did they get it? They got it at 2:50 p.m., right? They'd all just left modern geometry, was the class many of them took before this. Some of them took data ethics. So what we need to do is we need to add a character counter, and we need to add some squigglers. I'm going to allow myself a bit of a printf. A little controversial. I understand many of you only use put char and refuse to use printf under any circumstances, and I respect that a lot, okay? In fact, I expect to never see any printfs again in this class. And then we're going to have a line counter. We're going to len plus plus, and then if len equals 80, double equals. I know how to write code. Have you seen this one where you do the number first because you can't accidentally assign to numbers? Did they teach you that in school, or did you find that yourself?
I saw it on a YouTube short this morning.
Was it on my YouTube? Okay.
Every time I want to find your YouTube, I have to look for the one of the class recordings.
Yeah. So like Google is really mad at that account. I don't know what I did, because I have other accounts they're not mad at. If 80 equals len, put char.
They're like little entity fundamentalists.
I bet that's what it is. Does this look like it's correct?
Yoda notation. That's what they call the number first.
YouTube shorts are weird. I don't remember if there's a new line at the end. Should I put a new line?
Please do.
If you don't initialize ln to 0, is it automatically 0?
Should I initialize it to 0?
It's not automatically zero.
Okay,
Yes.
yeah, that is something. Yeah.
No, it should be 2, because of these 2 characters.
Oh,
The rare off by 2 error.
Writing my ternary program, but I keep getting off by 2 errors.
Has Jimmy been being a bad influence on you? It's quite close,
Oh,
right?
there's a dollar sign there somewhere.
Well, I think there's a possibility what's going on here is the standard is only defined for multiples of 32 bits, which means it's only defined for multiples of 4 characters. 189 is not a multiple of 4. Goodness sakes, that was hard to think through. I saw this error in class and I can't figure out what's causing it. Now I know. I downloaded this file on Windows, then pulled it over. So the line endings changed. I gained an extra character while this was passing through a different operating system. Where's my web browser? Do I have a web browser open? No, I closed it, right?
Oh, you have Firefox open at the top right of your alt tab thing there.
The color inversion's getting me. It's top right? Is that
Now it's on the top right. It's one row down to the left, all the way. Basically.
Got it, thank you.
Full Firefox.
Aren't you streaming again? Just from that
Well, I think I'm streaming, but I can't
Oh, the
tell.
stream doesn't have the color filter. Or
Oh,
maybe
that
it
is
does.
annoying. That's strange.
Oh no, I think that the stream might have the color filter.
Oh, it's just double.
Yeah.
It's double applied. Okay. That should work. Okay. No, I only care about repositories. Why would I care about me? Okay. Here's the code. Here's the Python file. I can grab the raw Python file. I can copy the link. I can tab back to the color filter is ruining me. No, that's the same one. This one?
Mhm.
Okay. No. What'd I do wrong? That should work, right?
Is that a private GitHub repository?
Oh, it's a private GitHub repository. No, this one is this one? This one's public, I think, right? Anyone in Discord?
No, it's not a public GitHub repository.
That's private. Okay.
Or maybe like, oh, I'm looking at the wrong account.
I expected this to work, right? Okay, so wget can do it, right? Oh, that one's got the extra character too. I edited the repo on Windows and recommitted it. That's the problem. Okay, how's head work? Why did that not work? Okay, there's, oh, base 85 got deleted, right? Move base 85.py.1, base 85.py. There's the head. Is that the first 188 characters? I can take the first 188 characters of this file, I can pipe it back into the file. What am I doing? Anyways, I think it's fine in the case where I have a multiple of 4 characters, but I can't generate a file with a multiple of 4 characters right now. Wait, I can open it in Vim. What am I doing? Okay, move base 85.py, base 8, nope, .1. Vim? Oh, I can just delete a line, right? Ah! No! Okay, I think we're cooked. See y'all next week. Yeah, wait. Do we have class next week?
Yeah.
The week after that is spring break? Yeah, next week is, it's cool stuff. I don't remember what it is. It's development instead of C before break.
We don't finish the big RSA before next week, right? Is that the next one?
No, it's due like Thursday after break or something. I broke it down into week chunks.
Yeah, and when you look at it, will this give me back? Okay. You were all dismissed. I'm going to keep talking. It's due April 3rd. And I have,
Yeah, I was just thinking that.
Maybe I should
Yeah.
download the office space and try and reference office space as many times as I can during the job interview, because their campus really reminds me of office space.
Really?
Yeah.
Yeah.
It's like the most depressing suburban office park I've ever
Yeah,
been in.
tell me that's
It's like, Calvin will know where this is. The open dental place is right after, like the Cougar Road exit. And it's so loud because it's like above the highway. And so there's no noise barrier.
it's so loud there.
It's louder than any airport I've ever been outside at.
Oh, yeah, Halo, if you're here, still here, thank you. Catch you.